Hello, everyone. Welcome to the tutorial today. Today, we're going to be giving an introduction, today and tomorrow, we're going to be giving an introduction to high performance parallel distributed computing in the Chapel programming language, UPC++, and Coarray Fortran. As you start to come into the tutorial, I recommend that you go to the link listed below, the go.lbl.gov/CUF23. At that link is going to be all kinds of instructions, most importantly, how to get on the Slack, because there you can ask asynchronous questions as those of us who are presenting are presenting. And you will also get all the information about how you can run the examples we'll be discussing on Performant or AWS or Frontier, if you have an account on Frontier. So my name is Michelle Strout, and I'm at Hewlett-Packard Enterprise. And I would like to thank folks at Hewlett-Packard Enterprise, HPE, and folks at Berkeley Lab, and Sorcery Institute, and NERSC, and Oak Ridge National Labs, and the ECP project for all the help that they've provided as we prepared for this tutorial. So I already introduced myself. Dr. Damien Roussan is also presenting today, and Dr. Amir Kamel is presenting as well. Other contributors to this tutorial are Dan Bonaccio, Jeremiah Corrado, Paul Hargrove, Catherine Rasmussen, Samir Shend, and Daniel Waters. Here we have an acknowledgement slide. We do appreciate the support of the ECP project and NERSC and Oak Ridge. So here's the schedule for today. So today we're going to go from noon to 3:15 Eastern time. We're going to start out with this 30-minute intro, and then I'm going to give a 20-minute intro on Chapel, and then we're going to have an intro for UPC++ and for Coarray Fortran. Where they're going to have a 15-minute coffee break from 1:30 to 1:45. And then starting at 1:45, it's going to be 90 minutes of parallel programming in Chapel. It's going to be fantastic. So as I said before, I do encourage that everyone go ahead and get on Slack. Here is the link on the right-hand side for that. And let me just show you what that is going to look like. Bring up the Slack. So in Slack, there's going to be the main CUF23 channel. And so the CUF23 is the short name for the tutorial today. There is then a CUF23 tech support channel. So that is to help you out if you're having any problems logging in, getting your AWS instance to work, getting Performant to work, etc. And then there is also a CUF Chapel specific channel as well. I think there's channels for the other two languages as well. I may just not have those up in my Slack. All right. At any point, we do strongly recommend that you put your questions in Slack. But if you do have questions and you're not in Slack, other options are you can raise your hand in Zoom. And then we can call on you and unmute you. And another option is to write in the chat in Zoom. But we do recommend that you ask in Slack first. The moderators are going to be looking at those Slack messages and bringing some of those questions to the speaker's attention as appropriate. Okay. All right, so let's get started. The main motivation to do distributed parallel computing in general is when you have a lot of data to process and analyze, or you have a very large simulation you would like to run, or both. You're doing both. And the kinds of resources many of us are working with is you have a laptop that has multiple cores, so you have parallelism even on your laptop, or your lab or institution could have a cluster that you can run on, or you could have access to a supercomputer of some kind. And one of the main goals for these parallel programming models is to try to make parallel programming a little bit easier, so that you can analyze that large amounts of data and perform large simulations significantly faster. So let's start out with a poll. We'd like to hear a little bit about all of you. There's 53 people on the call right now. Please go ahead and go to the Poll Everywhere link listed above. You could also use the QR code. You can see that we were, some of us were already indicating which programming languages do you use the most? So you can respond to this question up to 3 times if you would like. But let's see, as some of you start putting in the languages that you're using the most. All right, we're seeing some Python. It's like a little race here. All right, and thank you, Dan, for putting that link in the chat. I appreciate that. No Java. Okay, Java is getting no love whatsoever this morning. Oh, there you go. Somebody uses Java. All right. So this gives us kind of an interesting, a nice snapshot of where many of us are spending most of our time in terms of programming. A lot of C, C++, quite a bit of Fortran, significant amount of Python, some Chapel, a little bit of Java, some R, etc. All right, I'm going to go to the next slide, which is going to make this poll go away. So no more ballot box, Stefan. So let's talk about the programming models we're going to be discussing today. They're referred to as PGAS programming models, and that means a partition global address space. And so Chapel, UPC++, and Fortran with Coarrays are all considered PGAS programming models. And what it enables, these programming models provide an interface, and a programming model in general provides an interface and code patterns to a programmer, along with some concept of how the code is going to execute at runtime. And so across these 3 programming models, the model, the interface that we're providing to programmers is that you have this conceptual global address space. And then there are going to be separate processes that each have their own virtual address space as well. And each process is going to be able to access things in the global address space with code directly. And it's also going to be able to access its own local data. And so as we give the intros to the specific languages, we'll fine-tune this concept a bit to each particular language. But some of the key aspects of this is that you can access a variable in the global address space from each node if you're doing distributed computation over multiple nodes. And ultimately, that is implemented with puts and gets in the hardware. So these remote memory accesses. When you're accessing something in the global address space that isn't stored on the node that you're at, then you're going to have to go get that data or put to that data in a separate node. And in the partitioned global address space programming models, there's also various ways to partition and organize the data so that we can reduce the amount of RMA that's going on. So during this tutorial, we have a shared example program. So we have a 2D heat diffusion program that we've implemented in all three programming models. Then in Chapel, I'll also be showing you a k-mer counting example from bioinformatics, an image analysis example, and also how to process files in parallel. For UPC++, there's going to be a 1D Jacobi solver example and distributed hash table example. And in Fortran, it'll be the 2D heat equation, the shared example, and there's going to be some hello world variants. As part of this tutorial, we're going to have hands-on. Anybody can sign up for an AWS cloud instance. So please go to that link and you'll find where you can do that. You can also ask questions on the Slack if you're stuck. And then there's going to, some people have access to Perlmutter and Frontier. On Perlmutter, there's some guest accounts as well. So as we're going through the tutorial, we strongly recommend that you go ahead and give things a try as we're discussing. I already mentioned the Q&A protocol. I'll go ahead and mention again, there are more people online. There are experts available to answer your questions in Slack. So you can ask those questions in Slack. Some of those questions, the moderators might bring to the speaker's attention to be answered with the whole group. For the Slack, you should have received an email invite, or you can go to the link above. So let's talk a little bit more about these different programming models. One of the really cool things about them is there are production applications using these programming models. So for Chapel, there's CHAMPS, which is a 3D unstructured computational fluid dynamics code for simulating airplanes. For Fortran, Coarray Fortran, there's ICAR, which is a atmospheric research model. And one of the applications for UPC++ is meta-k-mer, which is a genome assembler application. And in the individual pieces of the tutorial, we go into a little bit more detail into some of these applications. So let's go ahead and start the hands-on part of the tutorial. So I'm going to go on to Perlmutter and step you all through compiling and running the hello worlds for all three programming models. Okay. So first, I need to go ahead and stop the share. Share. Okay. So I'm on Perlmutter. I've already downloaded the tarball that we're providing. And so I'm going to CD into the directory after unpacking the tarball. I have to actually spell the whole thing out. Inside this directory, you can see there is a README, there's a couple of source me's, and then there is a separate subdirectory for Chapel, Fortran, and UPC ++. I'm going to actually start out doing the source me. Okay, most of you are going to want the .sh. So you just say source me. That's going to do some setup and give you a little bit more instructions. And then I'm going to CD, let's start with UPC ++. And here we have some examples inside UPC ++. And if I do a make and then use the word run dash, and then use the prefix for any of these examples, the file name prefix for any of these examples, it's going to run the example. So let's start out with hello world. Ruh-roh. First snag. So let me try, is the link in the chat by any chance, Dan? To the tarball? Could you put it in there?
I will, yes. It's linked from the wiki page, but I will add the direct link.
Okay, yeah, I appreciate that. So you can either get it from the wiki page, or Dan's going to put it in the chat here. All right, so let's get an updated one. I think mine was outdated. So I'm getting an updated tarball. I'm going to remove the old directory just to be on the safe side. And then unpack the tarball. Go into the subdirectory again. Do the source me again. Okay, this is looking a little more promising. And then go into UPCXX. And do a make run. Hello world. All right. And so what those make files are going to do for you, and the mistake I ran into was not because of the tarball setup, it was just because I was using an old version. So that was all me. So first it's going to do a compilation of the hello world, and then it's actually going to run the hello world. You can see that the compilation is taking a little bit. We do have to get, we're going through SLRM and we're getting access to Perlmutter that way. So sometimes there'll be a little bit of hesitation there. So just let us know in the tech channel on Slack if you're having significant problems. Okay, so you can see the UPC XX Hello World was running on 4 processes, and it printed Hello World from those 4 processes. Now let's go to the Coarray Fortran directory. So we've got some Fortran examples in here, and then it's going to work the same way. You're going to say make run hello. And it has done the compilation of hello.f90. And then now it's running and using 4 processes. So you get the hello from 4 different images. And you, of course, can bring up Vim or some other editors that are available to see what the actual code looks like. So now let's go into Chapel. Here are all the Chapel examples. We also have a make file. You can do a make run hello. And there's a few hellos to pick from, so I'm going to do the hello par. And again, you see the compilation. This one ran with just one locale. So the number of locales is 1. If we want to actually see some parallelism in this one, I'm going to set the number of tasks per locale to something more than 1. And so I'm going to run hello par and say tasks per locale equals, let's do 3. Oh, you also have to tell it the number of locales. Okay, it doesn't want the equals after that. Okay. There we go. All right, so hopefully you all have had a chance to try out some of the hello worlds. Now let's go back to the introduction.
Got about 10 minutes left.
Yeah, thank you, Dan. Appreciate it. Okay, so now I have another poll for all of you. I think turtles was from our testing. So do you have any parallel programming experience? And if so, what tools have you used in the past? So this is a word cloud. So as you type in different types of tools that you've used to do parallel programming, they're going to show up in here. And so I'm just going to pause for about a minute to see the kinds of parallel programming tools you all have used. So MPI, yep, OpenMP, Tau, HPX. What else are we seeing? Coarray, Chapel, CUDA, Java, Cocos. Okay. Task flows, one I saw in there. Sickle, NVIDIA, HIP. See if I'm pthreads. Standard STD par. Actually, I don't know what that one is. TBB, Insys, NVSHMIN. All right, Ada. So lots of different ways that people have programmed in parallel before. Yeah, thank you for sharing all of those. Okay. So now let's talk about the shared problem that we've done in all 3 of these programming models. So it's 2D heat diffusion. The partial differential equation for it is in the upper right. If you want more about the mathematical details, you can go to the linked Wikipedia page there. And so we've taken that PDE equation and we've discretized it using finite differencing. We're going to set up some initial conditions for some square domain. And then we're going to take those initial temperature values, and then we're going to propagate them over time. And the boundary conditions are just constant boundary conditions. So on the lower left here, you can see the using the finite differencing to determine how we're going to compute a value of temperature, or U, at some time n+1 at a point ij. We're going to compute that temperature value using the previous temperature value at that same point that's stored in a different array. So from the previous time step, un. And then we're going to use discretized time and discretized space. So delta t and delta x and delta y for space. And delta t is our time. And we're going to look at neighboring values from that previous time step. So in the UPC++ and Chapel codes, we've simplified things a little bit by having our delta X and our delta Y be the same. And we've done some algebra to just have an alpha constant. And here is the simplified equation that we're going to be using. All right, so any questions at this point? So we've got about 5 more minutes of this 30-minute intro. Does anybody have any questions? I do see. Okay. So there is a question about linking to the Hello World examples posted here. I'll let Dan and others answer that. Thank you, Dan. All right. So now I have 3 questions for you about how you're programming. And so on the next slide, I'll start a poll EV survey. And so the questions you'll see if you go onto the poll EV survey are, have you used a cluster or supercomputer before? If so, what were some of their characteristics, like number of nodes, threads per node? We're all interested in hearing where you go when you have programming questions. Do you talk to colleagues, Stack Overflow, Google search, documentation? Maybe it's all of those. So we're interested in hearing about that. And then for your code, what computations and libraries are most important for your work? So let me go to that survey. And now that survey is active on Poll Everywhere. And you can kind of see over on the left some people answering. It's not going to show us any of the answers, but it's just giving us an indication of some people writing in some answers. So this would be a great time if anybody wants to bring up any questions, raise your hand. You can ask some questions in Slack. Moderators, are there any questions in Slack that we should bring up with the whole group?
I think there's a couple ongoing tech support discussions in the tech support channel.
Okay.
So if our center people, especially our nurse people, are watching that channel, that would be great. But probably not anything worth bringing up in the main discussion hall here.
Okay, great. And thank you for all of this participation I see happening on these Poll Everywhere surveys. Okay, I believe that this survey will stay live until we do another survey. So I'm going to go ahead and move to the next slide. Oh, this is the next survey. All right, so the other question that we have for you all is, what do you want to learn about Chapel, UPC++ or Coarray Fortran today? And so this one is a slightly different, it's not a survey, it's just a single question, and you can upvote. So you can give a star to things that are showing up. Okay, so we can have a little bit of which question are people most interested in. Okay, so there's a lot of just wanting to learn. Couple people want to see Coarray Fortran. Some people want to see how they differ and compare against each other. I think you'll get some of that. I think I see down at the bottom, somebody wants to see basics of parallel programming, get a little bit of that. Some beginning context to get started. And for those of you that are in this tutorial, this is a tutorial for beginning parallel programmers. We are assuming that that you've done some programming before and you have some interest in using parallel resources. But we're not assuming that you know how to program in parallel. Okay. All right. So thank you for all your responses. I am going to go ahead and go back to the previous slide to turn on that survey. So if you go to the Poll Everywhere link at this point, this 3-question survey will still be up. And I'm going to skip over the next slide so that that one stays up. I believe that's how that'll work. All right. So here is the schedule for today. What's up next, starting right now, is I'm going to give a 20-minute chapel intro, and then there's going to be a Fortran with Coarray's intro and a UPC++ intro. So each of these are going to be 20-minute intros. The link on the far right, this go.lbl.gov/CUF23, that's where you're going to want to go to find out how to get on the Slack, how to download the tarball with all the examples from all 3 programming models, and how to get started on either an AWS instance or Perlmutter, or if you have an account on Frontier. Okay. So I'm going to switch now to PowerPoint. Maybe.
Still showing your browser window.
Yeah, I'm not sure why I'm not seeing PowerPoint. Let me stop the share. There it is. All right, and we look like we're pretty much right on time, right on schedule. Okay, so here's an introduction to the Chapel parallel programming language. And this is, I put together these tutorial materials in collaboration with Jeremiah Corrado, who is on the Chapel team with me at HPE. So in this introduction, I'm going to talk a little bit about what Chapel is and how programmers are using Chapel in their applications. Talk some about the Chapel execution model with a parallel and distributed hello world example. I'll show you some pictures about the 2D heat diffusion example, some of the variants and how to compile and run them, although we're going to go into them in more detail in the 90-minute tutorial later today. And then the last slide in this 20-minute talk is learning objectives for today's 90-minute Chapel tutorial. So Chapel is a programming language that has been designed for ease of parallel programming, high performance, and portability. It's been around for about 20 years, so it's about 10 years younger than Python. And the way that Chapel is being used is it's being, some people are refactoring some of their existing codes and writing them in Chapel. Some people are developing new codes in Chapel. The Arcuda data analytics package is an interesting case. It's using a Python front end and then writing the backend server in Chapel so that Python users doing data science can get high performance computing and analyze tens of terabytes of data. There's also some examples of using Chapel at the high level to get distributed and shared memory parallelism, and then calling out to other processes. And then the other way around, taking an MPI program and on a single node getting shared memory parallelism using Chapel. So here are some pictures of the various applications being used. Many of these are being used in production. So if there are research applications, they're being used to actually produce papers and research. Arcuda is actually being used in production every day. That's the one of most use, and I'll show some highlights of that. If you want more information about these various applications that are using Chapel, there are links in these slides, so the PDFs are available on the wiki, that main link we keep showing you. And in this PDF, you should be able to get links to Chew, various years of Chew. So every year we have a Chapel implementers and users workshop. And these applications developers have presented their work at that workshop. So let me give you some of the highlights of these applications. So there's CHAMPS. This is a computational fluid dynamics framework for airplane simulation. And this was developed by Professor Eric Larendow's team at Polytechnic Montreal. It's over 100,000 lines of Chapel code right now. The performance that they've been able to achieve with this code has been competitive with other similar simulators from Stanford, MIT, et cetera. And by performance, I mean not only are they getting good answers in terms of the simulation results, they're also getting the performance and the scaling that they need. And the big difference that they're pointing out is the programmability. So this is a quote from Eric. We ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months now. So they're very happy with the productivity gains that they've gotten from doing this. And Eric will be the first one to tell you that as the PI, he wasn't the one that decided to switch to Chapel. It was the grad students and the postdocs just up and picked up Chapel and started writing their simulation framework in it. And now the whole team uses it. Arcuda is the data analytics framework that I mentioned before. This was developed by Mike Merrill and Bill Roos at the US Department of Defense. It is open source tool, so you can go download it. There's the link on GitHub right there. And what this is a Python front-end client and then a Chapel server that's able to process dozens of terabytes in seconds. And the next slide, I'm going to show you how on just this past April, we were able to get 1,200 gigabytes a second for argsort, which is essentially a parallel prefix sort on a system. And I also have even more results past that, newer than that. Another thing I wanted to point out, is occasionally we'll see journal papers or conference papers come out where somebody has used Chapel to do their science. The most recent instance of this is Marjan, where she used Chapel to create some calibrating hydrologic models. And so that's always to simulate watersheds. And so it's always nice to see people starting to use Chapel. All right, so here are those results I was talking about. And actually, I was just telling you about the April ones. The really impressive ones are from May. So on the graph, higher is better. Across the x-axis, we have number of nodes on a machine. So this isn't cores, this is number of nodes. And then the rate in terms of gigabytes per second is on the y-axis. And this argsort is a parallel radix sort computation. And in May of 2 years ago, we ran it up to 576 compute nodes on an HP Apollo. In April of this year, we ran it on a Slingshot 11, a machine with a Slingshot 11. So an HPE Cray EX and something with a Slingshot 11 network. We ran it up to 896 compute nodes. But then just a month later, so a couple of months ago in May, we were able to run it on something 10 times bigger. So something with over 8,000 compute nodes and achieved 8,500 gigabytes per second on this, on sorting in parallel. And the nice thing about this is we've got the performance and we've got the scaling here. but the number of lines of code for this computation doing this sorting is only about 100 lines of Chapel code. So we've also got that productivity.
About 10 minutes.
10 minutes? All right, great. Okay, so let's go through the Chapel execution model. So there's a key concept in Chapel called a locale. And a locale is something that's going to execute on a compute node. So in this diagram, if I've got 4 nodes, I essentially have a locale 0, 1, 2, 3. I have a locale on each node. And then when you run your program, you specify the executable, my Chapel program, and then you have to indicate the number of locales. Or if you saw me do the hello world, I used -nl and I specified just 1. But you could also specify 2, etc. All right, and in the program, we're going to have this locales array with a capital L. So you can actually refer to these different locations in the program. So let's look at how this turns out. Oh, and here's the key point before I show you some code. The main difference between the Chapel programming model and the other programming models you're going to hear about is the user's code starts running on just one locale. So it starts out with a single task on locale 0. The other programming models use what's referred to as single program multiple data, SPMD. And in those, you're going to have the same program start up on all of the processes. So the analogy here would be on all of the locales at once. Okay, so that's the main conceptual difference between the Chapel execution model and the other programming models you're going to be hearing about today. And also like MPI uses SPMD as well. Okay, so here's a program, a little Chapel program. This one's just doing shared memory parallelism, but it is referring to the current locale. So here is a keyword in as a key value variable in Chapel that refers to the current locale that we're running on. And then we're asking that current locale, how many processing units do you have? So think cores. And then that's how many tasks that co-for-all loop is going to start. So for every processing unit, it's going to start off a task and it's going to say hello from there. So a co-for-all loop, whenever it shows up, for every iteration of the loop, it's going to start an independent task. So if we run this program looking like this, we're going to see hello from each of the tasks on the node that we're on. So you can see the node name is the same, or the locale name is the same, N1032. So again, shared memory, not doing any distributed computing here. So now let's put an outer co-for-all loop around this loop. And this outer loop is going to do a co-for-all over all of our locales in that locales array. Okay. Co-for-all loops always create a task per iteration. So in this case, it's going to be creating a task per locale. And then there's this on loc statement block. And so what that on statement does is it essentially says, now I want this computation to occur on a particular locale. And so on each locale, you're going to have the co-for-all loop that's going to print a message per core as before. So now if we're running on 4 locales and have 4 tasks per locale, we're going to get like 16 messages out. All right, I saw Dan raise his hand. Dan?
Yep, we have a great question on Slack, which is a locale always a compute node or host?
That is a great question. So very commonly, we have one locale per node. But one of the features that came out in the March release, the June release of Chapel 1.31 is we can have a locale per socket on a node, and we also have the ability to have a locale per NIC. And so that is new functionality that we've been putting in recently. Great question. Any others? Okay. All right. So let's look a little bit at these heat diffusion examples. So in the repository, that tarball that you all were pointed at in the Chapel subdirectory, there's quite a few different heat diffusion example codes. The three that I'm going to be talking about today is the heat2d.chapel, which is a shared memory parallel version that runs on just locale 0. The heat2d dist, that's a parallel and distributed version, okay, that uses distributed arrays. And then the heat2d dist buffers. I'm going to just talk about the first two in this intro, and I'll get into more depth into that third one during the 90-minute. So first, let's just look at the heat2d chapel. So again, we're solving that 2D heat diffusion PDE. And at every time step, we're going to be computing the next temperature at every location in space. So the diagram over here on the left is showing how we're computing the next time step. So the UN+1 is being computed here by looking at the neighbors in the previous time step. Can you see my arrow, Dan?
I don't see it at the moment.
You don't see the arrow? Okay. All right. So the grid on the right is we're going to be computing new values into that. That's the UN+1 time step. And we're going to be calculating those values based on the neighboring values from the previous time step. And so you can actually see the Chapel code that does that update. It can be done in parallel. So we can, for each time step, we can compute all of the new temperature values in space all at once. And so that for all loop is doing for all ij in the indices inner. So on all of the inner indices, we're computing the next value of uij. And that's being done in parallel. And then in the code, you'll see that the output is a mean and standard deviation of all the values and time dissolution. For the distributed version that's in heat2d_dist, there we're actually taking the previous time step UN array and the new time step U array, and we're distributing those over our locales. And if you have the locales spread out over nodes, then you're going to get distributed parallelism. So let's talk a little bit about how that works. If in the previous version that's just doing a shared memory, when we declare the U array, we indicate what the domain, so const indices equals, and then we've got a domain specification there, 0 to nx-1 and 0 to ny-1. So we've got that two-dimensional domain, and then we're declaring that variable U as an array using that indices domain. So it's an array of reals. When we want to distribute the array, what we do then is we actually create, we still create indices the way it was before, but now we pass indices into a block.create domain. And so block is short for block distribution. And what it will do is it'll take those indices and it'll evenly divide them up in whatever dimensionality the original domain is. And so in this case, a 2D domain decomposition, and then store that domain decomposition in the capital indices. And so then we just declare our array with the capital indices. Was there a question?
I was saying we have about a minute left until we transition to the next.
About a minute left. Okay. All right, so we'll get into more detail on into how this works in the 90-minute. But now I'm going to finish up. There's a lot more parallelism supported in Chapel. Today, we're going to be mostly focused on the co-for-all and the for-all. So the stuff listed on the left is just for reference, and I'll have more code examples on those. And our learning objectives for today is to get more familiarity with the Chapel execution model. And then we're going to go through using a map dictionary to do k-mer counting, talk more about parallelism and locality in Chapel, look at how distributed parallelism can come about from decomposing 1D arrays and also doing block distributions over 1D arrays and 2D arrays in the context of processing files and the heat diffusion problem. And then we have a coral reef diversity example for image processing. And then some about GPU parallelism at the end of the 90 minutes. And we'll wrap it up with how you can participate in the Chapel community. But with that, I'm going to pass things over to, I can't remember who's next at this juncture.
Damien Roussan is
I am.
next, and he'll be talking
Damien.
about
Okay, Damien
Fortran
Roussan.
Okay.
Yes.
Coarrays. And there will be another Chapel session later in the day. So if you're here for Chapel, you're going to get a lot more Chapel later today. But we're going to give now an intro on Coarray Fortran, and then there'll be an intro on UPC++.
Okay, thanks, Dan, and thanks, Michelle, for the great start for the day. So we're covering Coarray Fortran now. I'm Damien Roussan, and I'm the group lead for Computer Languages and System Software group at Berkeley Lab. And in this 20-minute overview, I'll first give you an introduction to Coarray Fortran. It's oftentimes abbreviated with the acronym CAF. And depending on the audience, it's sometimes important to talk about why Fortran matters. Fortran is the first widely used high-level programming language invented in 1957 at IBM, but still constantly being updated. I sit on the committee that develops each new version. There's a new version coming out this year that'll be called Fortran 2023. That's fully object-oriented, parallel, interoperable with C, lots of other great features. And some acronyms here that you're familiar with from Michelle's talk earlier. We'll talk about SPMD parallel execution, single program, multiple data, and PGAS data structures, as well as remote memory access, one-sided communication. So then I'll wrap up by showing you the heat conduction solver, analogous to what you saw in Chapel, and show you how to compile and run it, and hopefully how to understand it. So this is an interesting slide in terms of just choosing where and when to present it. I just gave a talk at a conference in Switzerland last month. And at the end of my talk, one of the speakers said, you know, you don't really have to show this slide around here. So there's a lot of variation in the usage of Fortran. There's regional variation. I've seen data from a supercomputer center in the UK that 85% of their cycles are occupied by Fortran codes. It's pretty widely accepted and used in Europe and Japan as well. And also there's variation across disciplines. I often say that if your field embraced computing early, there's a good chance there's a lot of Fortran in the field. So weather and climate, every time you look at a weather forecast, you're looking at the results of a Fortran code, guaranteed. If you look at what's happening with the global economy and how much that's being impacted by climate change, most of the agreements that we're making, all the agreements that we're making based on climate across countries are being made based on the predictions of codes and observations. And those codes are Fortran codes. In addition to working at Berkeley Lab, I lead a business called Archaeologic. And our biggest client is the Nuclear Regulatory Commission, which is essentially a Fortran shop. There are a lot of, so there's a lot of organizational variation as well. The code on the left is developed at the National Center for Atmospheric Research, which again is essentially an all Fortran organization. On the right, you see an aerospace application here, Fun3D, that's developed at NASA Langley Research Center. That's the site of the movie Hidden Figures, if any of you saw that movie. And that Fun3D code has been used by a number of companies in industry, SpaceX, for example. So lots of important stuff happening with the Fortran language. So Coarray Fortran, to understand the background of what brought the language to this point. So Fortran became parallel in the 2008 standard. And that was based on features that were developed by Bob Numrek when he was working at Coarray back in the 1990s. And then he worked with John Reed, who was on the Fortran committee, to bring the features into the Fortran standard. And the basic idea that inspired Bob was, what's the smallest number of changes I can make to the language in order to take it parallel without requiring people to learn a lot new and change a lot of the rules of that they're used to working with in Fortran. So the early work in Coarray Fortran goes all the way back to 1998. You can see Bob prefers a different spelling, co-array. And that feature set that came into the language in 2008 has now also been greatly expanded in Fortran 2018. So you'll be seeing features today and tomorrow in Coarray Fortran that are, at the leading edge of the language. Some of them are from the latest standard, Fortran 2018. So the single program multiple data, since you've been introduced to this already, my primary goal is to explain the terminology that Fortran uses for this, and some of the things that are unique about that. And in particular, the way a parallel Fortran program starts is that there's a synchronized launch of multiple images. And the standard committee is actually careful never to tie the word image to a specific technology. So each compiler or runtime library can choose how to actually support images, which are basically copies of your program. An image could be a process, or in shared memory, it could be a thread. If the compiler is supporting the Coarray features using MPI, which is the case if you're using G-Fortran and the parallel runtime library Open Coarrays, for which I lead the development, then an image might be an MPI rank. Once the images have each launched, then they execute asynchronously. So there's no coordination or meeting up of the images at a given point in time, unless the programmer explicitly does something to synchronize. At the end of the program, there could be an error termination that one image can initiate, and then all other images would shut down as soon as possible, or a normal termination, which is also a synchronized process, so sort of a three-step process where each image reaches the normal termination point, waits for the others to get there, because you want to make sure that data doesn't go away that other images might need, and then the shutdown process can start after each image gets there. So here's a very simple hello world program. I'll show you one way to run it in a moment. You can also run it using the commands in the upper right. Just make run-hi. So this program is simply printing out a greeting that is which image is doing the printing, and it also contains the number of images. So when I compile it at the command line, I usually, let's say if I'm using G-Fortran and Open Coarrays provides a compiler wrapper caf. And so in the first line there, I'm compiling with caf and telling the compiler to name my executable program hi. And then there's a program launcher, caf run, and these are wrappers around. So caf is a wrapper around MPI fort in this case, and caf run is a wrapper around MPI run or MPI exec. And I'm saying that I'd like to launch 7 images. Now, because I didn't do any sort of coordination across the images, and actually it turns out for reasons related to IO, even if I did, there's really not much that I could do to order the messages that we're seeing here. So you can run multiple times and get different ordering of the messages as they appear. You can see a somewhat random number ordering in the first run, and then they happen to come out sequentially in the next one. So to think through how this works, each image is an independent copy of your program. And there's a timeline here on the left, so time increases as you go down. And the images will all start on their own, but no actual executable statements will execute until all of the images have started. So that implies that there needs to be a barrier in place. And so that as the program launches, at some point, each image waits until all the images get to this barrier. This would be set up by the compiler. It's not something that you have to explicitly do. And once they get past that barrier, then they'll each do their print at whatever time they reach the print statement. And then once they get past that print statement, they'll reach the end program. And now we're doing what I just described as normal termination. So normal termination then involves a barrier, as I talked about. So they'll each wait until every other image gets to that barrier. And that means then that an end program statement is an example of an image control statement. So the basic idea is summarized at the bottom. After the creation of a fixed number of images, each image's first segment executes. A segment is a sequence of statements. Image control statements totally order the segments executed by a single image, and partially order segments executed by separate images. We'll see other forms of image control statements as we go here.
Got about 10 minutes.
This is a slightly more involved Hello World program where now I'm having image 1, which I'm designating as the writer, grab the greeting from each image and print it out. At line 8 here, I have an associate statement. That's something that I like to use because it's inspired by the functional programming style. If I associate with an expression, one simple example of which is a function result, then I get immutable state. I get something that can't be changed. So it means that I can't accidentally change this variable. So there are compile time constants, like at line 4, where I give something the parameter attribute that says this is known at compile time and won't change. At line 8, I like to refer to those as runtime constants. This is a value that I can't determine until runtime, but it's not going to change within this block. So at line 10, I'm doing what's called internal file IO. Essentially, that means I'm writing a message into a string instead of writing to an external file. Jump back up to line 6. Because I know I want to do communication of these greetings, I'm declaring the greeting as a coarray. The square brackets in Fortran are the dimensions that you use for a coarray. I don't get to give a specific dimension there. That's why you see the asterisk, because that will get determined by how many images I launch. So that will range from 1 to the number of images. However, notice at line 10, I don't show the square brackets, because if I only want to work with local data, then I don't need the square brackets. And then I have a sync all statement. So that's a global synchronization point. So every image will stop at that point. So now I know all the images have been created. And then at line 13, if I'm the writing image, image 1, then I'm going to loop over all of the greetings, all of the images. And at line 15, grab the image from whichever, grab the greeting from whichever image has it and print it out. So that's where you're seeing the remote memory access or one-sided communication. We're getting data from another image. To run this program, again, you could use the make command like I showed earlier. I usually just compile directly, and this time I'm running it in 5 images. And now we can see that both times there's a definite ordering of the messages, and that's because we had a loop there. When you write a loop, you're explicitly telling the compiler, I want to do these passes through this loop in this order. We'll talk about a way to write loops that doesn't involve explicit ordering a bit later. So this is how you would run the heat equation program. You can also use a make command that I'll show you a bit later. And this program, I think I'm running in 4 images. And if I recall correctly, let's say it takes around 7 seconds to run. I'm doing this on Mac OS on my laptop. Because there's MPI under the hood and MPI might access the network, there's a security feature that requires you to say yes to this dialog box for each image. And then I compute an average temperature at the end. So this is, again, a 2D domain with fixed boundary conditions. One difference between this solver and the other 2 languages is that I'm applying at the initial condition a uniform temperature internally, whereas the other solvers use a smaller square where they apply that temperature. Dan, you have your hand up?
Yeah, so there's a great question in chat about whether Coarray Fortran in general requires MPI. They were asking specifically about CAF and CAF run, but the question is, I think, an interesting one in general.
Yes, that's a great question. And I'll talk about this some tomorrow. There are alternatives. There have been Coarray Fortran implementations that run on top of threads. So Open Coarrays at one time had an alternative where you could use GasNet, which is developed in our group class here at Berkeley Lab. And we're currently working on a new runtime library we call Caffeine, the Coarray Fortran framework of efficient interfaces to network environments. And that caffeine also uses GasNet. And we are proposing caffeine as the runtime library for the LLVM Flang compiler. So hopefully that will be adopted. There have also been, OpenCoarray's also had an implementation based on OpenSHMEM. So one of the really nice things about the Coarray Fortran approach is that you can actually make, in some cases, a link time decision, to switch between MPI or GasNet or OpenSHMEM, if your compiler and runtime libraries provide those options. And you can do that without changing a single line of code. I'll show an example where that becomes really important tomorrow. So this is the heat equation. It's a partial differential equation. You don't really need to be familiar with PDEs, for this tutorial. But for those of you who are, you'll recognize that equation. And the way that we solve it is that we choose a discrete grid of points of temperature. And I'm using curly braces there to indicate that I'm working with an array of temperatures on that grid. And we get a value at a new time step n+1 based on updating the value at the old time step n. And our increment is the delta t, the time step, times alpha, the thermal diffusivity, times the Laplacian of the old temperature. The alpha that's defined in the Fortran program is the one that you would use in heat diffusion, which would be different if you're solving a different type of diffusion problem. And it also differs from the alpha that's used in the other two programming languages, where those actually absorb the delta t into the constant. So then one of the things I really like about Fortran's approach is that you can get a really nice correspondence between the syntax that you would write in a textbook or on a blackboard to the syntax that you have in the program. Michelle mentioned earlier computational fluid dynamics as one important application for parallel programming. And I often point out that if you took a student who had studied fluid dynamics, but not the computational part of it, and you marched them over to a screen and showed them a computational fluid dynamics code, in most cases, they really would not see anything that they would recognize from the textbook. But because we can define our own operators in Fortran, we have the ability to give this correspondence. And so the T variables here are local objects. There are different ways you can do this. You can also define distributed objects. We'll see how to do that a bit later. But in this case, I'm just working with local data. And each of the operators then is actually a user-defined operator. And that includes the overloading of the plus and the times, but also of the definition of a new operator, Laplacian.
About 2 minutes.
This 2 minutes. This is a class diagram that just gives you an idea of what's in the one core data structure, the one class that's in the Fortran code. So it's a 2D subdomain so you just have the name of the type in the first panel there, and then the data that's inside of it. This is using what's called the unified modeling language. It's just a way to graphically depict what classes in an object-oriented program. And so you have a real array. It's actually a 2D array. And then several procedures that are part of that class. One that defines the values and various ones that implement these operators or return various values. So to see how this works, and we'll have time to get into more detail on this tomorrow, we break the problem up into various subdomains. Between each of those domains, we have a halo. The reason it's called a halo is that in this case, we're only partitioning along one coordinate direction. But if we were partitioning along two directions, then you'd see a halo region around the subdomains. And at some point in the code at the bottom here, we do what's called a halo exchange. It's a very common operation in PDE solvers. And the basic idea there at line 234, as long as I'm not the rightmost domain, I'm going to put data to my left, or I guess the leftmost domain, I'm going to put data to my left. And as long as I'm not the rightmost domain, I'll put data to my right. And I'll have more time tomorrow to show you some more detail about how that works. Last thing I want to mention is that there's also a set of features in Fortran that help with more fine-grained, let's say, loop level parallelism. And this is showing some performance analysis results from an open source package, the Tuning and Analysis Utilities, TAO. And the blue highlight there is showing me that line 188 is the costliest line in the program. And when we look down, we see that that's a do concurrent. This is a type of looping mechanism where we're not telling the compiler that the iterations through the loop are ordered. And that therefore means that there are all kinds of opportunities the compiler has for optimization. One of the most exciting ones these days is the opportunity to offload this computation to a graphics processing unit, which is where a lot of the computing power is on the high-end platforms that you have access to in this tutorial, Perlmutter and Frontier. So I think I'll reserve these. I have a few comments here about the Fortran, the Coarray Fortran model, and how what's attractive about it and how it works with legacy codes. But for now, I'll stop there and hand off to Amr.
Thank you very much, Damien. So as you mentioned, there'll be a 90-minute session tomorrow dedicated entirely to Fortran. So if we piqued your interest, please come back tomorrow to see that. And now we'll have Amr Kamal from LBL talking about the UPC++ library. Looks good.
Thank you, Dan, and thank you everyone for attending this tutorial. My name is Amr Kamal. I'm visiting faculty at the Lawrence Berkeley Lab in Damien's group, and I work on library design and implementation of UPC++. There we go. So I'll start off by acknowledging everyone who's contributed to the project and has collaborated with us. This includes people who have directly contributed to the design as well as the implementation, and folks who've implemented applications that I'll be talking about tomorrow in the main UPC++ presentation. So at a high level, kind of the big things that UPC++ offers is features for parallelism and asynchrony. And the two big features that it provides are RMA, which you've seen in the other models. So the ability to do gets and puts to remote locations located in on other processes, and to do this using low overhead constructs. And then the other big feature is remote procedure call. And so this is the ability to move computation as well as arguments to where the data might be located. And so this has some similarities to the on construct that you saw in Chapel. The library as a whole is designed with performance in mind, both in terms of the implementation as well as the user abstractions it provides. So in particular, communication is explicit, so that if you're actually looking at UPC++ code, you can sort of visually see where communication is happening and what might be expensive in the code. Communication is also asynchronous, so there's a separate initiation of the communication, and then you can later on, ask whether or not the result, whether the communication has completed. And so this allows you to overlap different communications with each other or with computation. And then we really focused on trying to make the library scalable to large numbers of processes. And so this means that we spend a lot of time making sure that our memory usage is as small as possible, and also the constructs that we provide can also scale. And kind of our reasoning behind designing the library in this way is primarily around applications having some sort of irregularity. And so some examples of this are adaptive meshes, for instance, in AMR EX. And what adaptive meshes are is that you have some physical domain that you're simulating, and there might be some interesting behavior in some parts of the domain and less interesting behavior in other parts of the domain. So where there's interesting behavior, you might have higher resolution grids compared to where there's less interesting things going on. And so that means that you have when processes need to communicate with each other because of these grids, you can have different amounts of data, and you can have different processes needing to communicate with each other based on who owns what portion of each grid. Along the same lines, sparse matrix applications, you also have matrices that have a lot of non-zeros in some locations in the matrix, and then in other parts of the matrix, they might be mostly zeros. And so again, we have some irregularity in terms of the data layout. And then there's things that are inherently irregular, like hash tables, where the location might depend on a hash value that you may not know until runtime. Graph analytics, where you might have some sort of irregular graph, or dynamic load balancing between different processes. And so the common theme with this irregularity is that you have, in at least one dimension, something that's unpredictable. So this could be space in terms of which processes need to communicate with each other. Time, which could be when those processes need to communicate, and that might actually depend on something to do with the data. For instance, in a hash table, if you want to insert some key value pair, you hash the key, and then it might be on some other process, and at that point you might need to communicate. And then also volume, or just the amount of data that needs to be communicated, might also differ. And so what we need is, we need constructs for irregularity to essentially support, we need constructs for asynchrony to support doing this irregular data movement efficiently. We also see some system trends that are making asynchrony more and more important as well. And so the big, trend is that computational resources on a node tend to have been increasing, especially with GPUs and other accelerators. But latency of communication isn't really improving at the same rate. And so essentially the cost of communication compared to the cost of computation has become more and more important. And so since that's the case in terms of the hardware that we see on these big exascale systems like Frontier and Perlmutter, we need to do more work in the software to essentially reduce the communication costs. So things like overlapping communication to hide latency, reducing memory usage, communicating more frequently so that more things can be overlapped, and then also lowering the overhead that the software itself incurs. And one thing that's common amongst all the models that you've seen today is we primarily rely on one-sided communication to minimize the overhead. So a lot of you have had experience with MPI, which has both two-sided as well as one-sided support. In a two-sided model, essentially both the initiator of the communication and the other side sort of need to coordinate for that transfer to happen. So this little cartoon over here kind of demonstrates at a high level what needs to happen. So we have a message that has some sort of metadata. Here I'm just abstracting it as a message ID, as well as the data payload. And so the initiator sends it over across the network, and the network controller on the target receives the data, moves it into a buffer, and then the host CPU needs to be involved on that target to actually move it from that system buffer into the user side. On the other hand, when it comes to one-sided communication, essentially all the metadata is provided as part of the message. And here again, I've abstracted that into the address on the target process where that data needs to go. And so when the initiator does the transfer, again, once the NIC on the target receives that, modern hardware has the ability to just directly transfer that into the target memory location on the host without the involvement of the host CPU. And so this has benefits for performance in that it matches what the hardware already supports. It also has benefits on the software side of things, and on the programming side of things, we don't have to worry about messaging arriving out of order. We don't have to worry about unexpected messages because we don't need to coordinate on both ends. And as a whole, this looks a lot like shared memory. And so just quickly illustrate sort of the benefits of one-sided communication and also using a low overhead communication library. Here we have a comparison between GasNet-EX, which is the communication library that UPC++ uses under the hood, with both one-sided and two-sided MPI. And it might be a bit difficult to see, apologies for that. There's this sort of green line over here that might be difficult to see depending on your monitor. But that's the two-sided MPI, which for medium-sized messages does worse in terms of flood bandwidth on the right-hand side over here on these two machines. And then even when it comes to one-sided MPI on some machines, GasNet-EX has lower overhead, so it's able to more quickly reach peak bandwidth on a machine. On the left-hand side, we see the other side of the equation, which is latency, how long the communication takes. And so here we have a small message size. And again, I'll remind you that one of the things that I mentioned is that smaller messages are becoming more and more important. And then what we see is that on all four of these machines, GasNet-EX actually incurs lower latency than even one-sided MPI.
About 10 minutes.
All right, thank you, Dan. So, you know, the one-sided communication is the primitive on top of which we build the programming model. And you've already seen Chapel and Fortran that have this partition global address space model. UPC++ does as well. And in UPC++ specifically, what we have is the memory on each process. There's a private segment, which is only accessible to that process itself. And then there's a shared segment, which can be accessed by other processes as well. Go ahead, Dan.
There's a great question in Slack, which is UPC++ built on top of MPI?
So good question. UPC++ is built on top of GasNet. Now, GasNet does have support for running on top of MPI if that's what you have at the network layer. But GasNet also supports other network layers, like even just UDP or InfiniBand or other networks as well. All right, so going back to sort of the UPC++ flavor of PGAS. Again, we have these shared segments and they comprise the global address space. And then the way that as a programmer, you access something that lives in a different process's shared segment is through what's called the global pointer. And so, you know, this is similar to a normal pointer or a reference if you've been using Python instead. Except for it has both the location of the object in whatever on whatever process is located, as well as information about the process itself. And so we refer to that as the affinity, and that's essentially the process that owns that object. And you know, just for completeness, I want to mention that we've seen Chapel, Coarray, Fortran, our PGAS languages. UPC++ is a PGAS library, and there are others as well. All right, so PGAS is the memory model. The execution model of UPC++ is like MPI and Coarray Fortran that Damien already described, which is the SPIMD model of execution. And so what this means is that you have a fixed number of processes and the program starts running on all of them. Here we have a simple hello world in UPC++. And because UPC++ is a library, the first thing we have to do is initialize the library just to start it up. And then, once the library has been initialized, each process proceeds past that. And as Damien mentioned for Coarray Fortran, this is asynchronous unless you explicitly synchronize. And so here we have a printout where each process prints out its process number. And so these prints happen in parallel asynchronously, and they can appear in the output in any order. And then we have a barrier synchronization, which stops anyone from proceeding until everyone has reached it. And then the next statement, the process whose process number is 0 does its own printout. And because we have this explicit barrier synchronization between that print and the previous ones, we're guaranteed that that print will happen after all the other ones have completed. And then finally, we have a finalized call to shut down the library. All right, so a little bit more on global pointers. So I mentioned that they're similar to what we refer to as raw pointers, or again, in the Python or Java context, what they would call a reference. But what this does is it allows us to have one of these pointers that actually refers to an object that lives in a different address space. In C++, we use the template syntax. So we have global pointer as a template, and then it's parameterized by the type of the object that it points to, such as double or a node object. And in this diagram, what we have is that we have a linked list that's distributed across multiple nodes. And so we have some next pointers that are pointing to nodes that are located on other processes. And then we also have some pointers that themselves live in private memory, but point to an object in shared memory. And then we can also have just regular raw pointers that refer to something in the process's own memory, or in the case of UPC ++, a raw pointer can also refer to something on a different process that shares memory. So we do have optimizations for co-located processes. It's not something that we'll have a chance to talk about at length in this tutorial. All right, so in terms of implementation, UPC ++, unlike Chapel and Coarray Fortran, it's a library as opposed to a language. So the main benefit of this is that we can leverage standard C++ libraries, and programs can easily use anything that's written in normal C++, including the standard library or other C++ libraries. As I mentioned previously, we rely on GasNet-EX to provide the network primitives. And so this abstracts the network hardware for us, and also provides something called active messages, which are sort of a restricted form of remote procedure call on which we build the more general UPC ++ version. And UPC++ is also designed for interoperability. So it uses the same execution model as MPI, which enables hybrid applications or allow you to port an application from MPI to UPC++ piecemeal. And then it also interoperates with on-node compute models in the same way that MPI does.
So we've got about 5 minutes left, and we've had some interesting questions in the Slack, but I don't think we have a lot of time for verbal questions right now. So maybe during the break, we can answer some more questions.
All right, thanks, Dan. And just I want to briefly illustrate that even though we have UPC++ implemented on top of GasNet, we see that UPC++ itself adds little overhead on top of GasNet. So we saw previously that for medium-sized messages on the Coarray machine, GasNet provides both better latency and bandwidth than one-sided MPI, and we see that still holds for UPC++ as well. So I want to take a couple of moments to just talk about sort of the main features for asynchrony. And again, this is just going to be a brief overview. Tomorrow we'll go into much more detail and see a lot more code in terms of how to use these. And the first big feature that I mentioned was RMA, or one-sided remote memory access. And like other communication operations, this is asynchronous. So we have an initiation, and then later on, we can wait for the result. So in this example over here, we might want to retrieve some value that's located on a different process. And so we would have a global pointer that's pointing at that object. And then we can do a remote get or an rget on that global pointer. What we get back isn't the integer itself, but it's something called a future that represents both the integer value and also whether or not it's ready, whether or not the communication has completed. We can then go ahead and do some other work, either communication or computation, to hopefully overlap that communication. And then when we actually need it, we can do a wait on the future. In the ideal case, the communication is completed and we don't have to actually wait at all. But if it hasn't completed, then we'll wait for it to complete before giving us back the result. The other big feature is remote procedure call. And again, this is asynchronous. So we initiate an RPC, giving it the target process on which we want the computation to run. We also give it the function object that represents the computation, and then any arguments we want to that function. And so this, again, it initiates a transfer to the remote process of both the object itself and the arguments. And then at some later point, the target process will execute that computation and send a notification to the initiator that it was done, along with any return value. And as with RMA, what we get, what the initiator gets from the RPC is a future that represents both any result values and the completion of the call. And then, when the completion actually happens, then we can actually obtain the result, again, by calling wait, for instance. And as with RMA, this is designed to allow you to overlap remote procedure calls with other things, including other remote procedure calls. All right, the last thing I want to talk about is the 2D heat diffusion, which you saw in both Chapel and Coarray Fortran. We won't actually look at the details of how it's implemented today. We'll do that tomorrow. But I'd like to give you all a chance to actually run it and maybe try some experiments with it. Okay. So I'm actually going to switch to a terminal so I can show you this. All right. So here I've downloaded the tutorial materials and followed the instructions to do that. Again, go.lbl.gov/CUF23. And so right now I'm in the CUF23/UPCXX directory. And if I do an ls, which lists the files in this directory, I see that we have heat2d.cpp as the heat equation example. Okay, so to run it, we prepend that with run dash heat2d and then without the .cpp. And so what this will do is it'll compile it if it hasn't already been compiled, and then it's going to run it with some default arguments. And so here we're running it on 4 processes, and then with the default domain size, which is 4096 by 4096. Okay. So if I want to run it with, say, a different number of processes, say 2 processes, I can copy that command and paste it and just change the value after dash lowercase n to 2. And then, it takes about twice as long with half the number of processes as we would expect. Then I can also run a bigger problem size. And again, the default is 4096 by 4096. So let me increase it in both dimensions by 2x. So, I would expect this to take about 4 times as long because the problem is 4 times bigger. And we see that this happened to be the case on my machine. And then if I increase the number of processes, hopefully it should get faster. And so this is, by the way, this is running on my local machine, which is a Mac Mini. It has, I think, 8 performance cores. So if I go up to 8, hopefully it'll get faster. It won't be quite twice as fast once it gets to the larger sizes. And here it ended up being about 10% faster. Yeah, and by the way, when I did this offline, it was about 50% faster. I think running Zoom and everything else is using up a lot of the cycles on my machine, which is why we're seeing only about a 10% decrease in running time. Go ahead, Dan.
So we have a 10-minute, or we had what was a 15-minute break and has now been reduced to a 10-minute break scheduled. So I think this is a good point for if people need to get up and use the bathroom or get a drink or whatever, they can do that. I think the presenters, if they're still here and available, can continue to answer questions. We've had some very interesting questions in Slack, which we could talk about, but we are gonna break the presentation here, I think, and then reconvene at 1:45 Eastern, where Michelle Strout will be talking about Chapel.
Thank you, Dan, and thank you everyone for attending the tutorial today.
So one of the interesting questions that I had in Slack that I'll throw open to, I guess, all the presenters or whoever wants to talk first is a general PGAS question about how does the stack and heap memory of a process relate to private memory and global space memory? Amr, you want to take a crack at that?
Yeah, sure. I'll start with the UPC++. So in the UPC++, we have an explicit distinction between private and shared. And so by default, things are in private memory. So this includes both stack variables as well as if you just allocate something using the normal C++ allocator. So using new, for instance. And then to allocate something in shared memory, you have to do that explicitly. And so the UPC++ library itself provides allocation templates for constructing an object in shared memory.
Damien or Michelle want to answer for your models?
So I should say I'm a mechanical engineer by training, computer scientist by trade. So I don't know that much about compiler design. I'll say there are two types of Coarrays that are relevant to this discussion. Yeah, there are static Coarrays that you can declare, let's say in the main program, and then there are Coarrays that you can declare inside a procedure. So if I'm interpreting the terms correctly, and I'll expect a computer scientist to correct me if I'm not, I would imagine that the ones in the main program that are static would be allocated on the heap, and the ones that are inside a subroutine would be allocated on the stack. Did I get that right? Dan, what do you think?
Yeah, I think that sounded right. Michelle, would you like to talk anything about the model and
Sure.
how it relates to?
Yeah, so I think in Chapel, it's when you declare and initialize a variable, it's going to be allocated on whatever node the current locale is sitting at, unless you declare a distributed variable of some kind. And then that'll be allocated across locales. And then, but in terms of, so that's where it's allocated. So it's either allocated in the current locale or across locales if it's a distributed object. In terms of where is it visible, UPC++, it sounds like the default is that things are private. In Chapel, it's the opposite. The default is that variables are global. And so you're going to be able to see that variable in a whatever lexical scoping, if it's visible in the typical lexical scoping you have in your program, then you're going to be able to access that variable, even if it actually lives on a different locale than what you're currently executing on.
All right. So there's a question in the UPC++ channel for Amr about, are there constraints on the function arguments for RPC? For example, do the arguments have to be trivially copyable?
They don't have to be trivially copyable. They can be, but we actually have a serialization interface that allows you to provide things that aren't necessarily trivially copyable. So I should say that this isn't something that we're going to get a chance to talk about in detail in this tutorial, but we can be happy to discuss it offline.
There was at least one question that I saw in Zoom chat and also in Slack, which is details about how barriers work, basically. So does anyone want to take a crack at explaining the control flow for a barrier?
Dan, you might be the best equipped to answer that question.
Yeah, there we go.
So I think we had a pretty picture of this in one of the slide decks. I don't know if it's handy, but basically the idea with the barrier is all of the processes or images call into a function. And the simplest form of a barrier is a blocking barrier, where all of the processes will basically sit inside of that call, that barrier call, until all the other ones have arrived. And then when all of the processes have arrived at the barrier, then they synchronize with each other over the network, and the details of how they do that is very dependent on the hardware. But once they have established that everybody has arrived at the barrier, then they all return together. Thank you, Damon. So that's kind of what that brick wall shows, is that they all reach the brick wall, and then none of them leave until all of them have arrived. So the power of this is that after the return from the barrier, they can all infer that anything that was executed before the barrier is complete. And in the case of operations with side effects, for example, on the global address space, you can know that those side effects that were performed before the barrier are now visible to everybody after the barrier. So that's kind of the simplest form of barrier. There's also non-blocking barriers and team barriers that you can do over a subset of the processes, but this shows kind of the general idea.
All right, I'm going to go ahead and get started. We're at 45 after the hour. And so this is the 90-minute session on programming in Chapel. So we're going to be looking at how to compile and run Chapel programs, doing some more slides that work towards having you be familiar with the Chapel execution model. So how codes run in parallel and in serial on one node, across nodes, and both. And then the examples that we're going to be going forth to learn these concepts. We've got a serial code using map and dictionary. So this is k-mer counting from bioinformatics. We're going to talk quite a bit about parallelism and locality in Chapel. And then look at, for both 1D arrays and 2D arrays, how distributing those can provide distributed parallelism and shared memory parallelism. And that we're going to look at the processing files in parallel example, and also a heat diffusion problem. For image processing, we have an example that has both distributed parallelism and shared memory parallelism by breaking up a 2D array, and that's a Coarray diversity application. And then I've got some slides on what the current GPU parallelism support is in Chapel. And we'll wrap up with how you can get help and how you can participate in the Chapel community. So during the tutorial today and tomorrow, all of the examples and the instructions on how to use the AWS images and the and Perlmutter and even Frontier are located in the tarball. The link is on the screen, and you can get that tarball with a curl command. You can untar it and then CD into it. So from this point forward, I'm going to assume that you've done that. So when we're looking at code examples, I'm going to assume you've gone into the CUF23 subdirectory, and for this part of the tutorial, you've gone into the chapel subdirectory. So for after the tutorial, those instances and reservations won't be available anymore. But I imagine everyone is going to want to continue to program in Chapel. And so to continue to try Chapel out, I think the lowest overhead way to do that is there's Chapel is supported on the Attempt This Online webpage. And so you can go to our main website, chapellang.org. And then there's an Attempt This Online little icon in the lower left. You can click on that and you can put in Chapel programs and see what the output is. You can also use a Docker container on your laptop. And below are the commands for how you pull that Docker container and use that Docker container to run or compile and run Chapel programs. All right, and thank you, Jeremiah, for putting up that link. Another thing I recommend that you do at the beginning of this tutorial is once you've gotten that tarball and you've gone into the Chapel subdirectory, then go ahead and open up the Chapel quick reference.pdf. That's going to show you, give you a nice overview of all the different kinds of statements and expressions and commands in the Chapel programming language. Okay, so let's start with the serial code example where we're doing k-mer counting. So I'm going to talk through the code on this slide, and then on the next slide, I will actually move over to a terminal window and we'll start trying that out. We'll do a demo. So on the left is a full Chapel program. The top of that, you can see the use statement, and that is bringing in two standard libraries in Chapel, the map standard library and the IO. The map standard library, or module, as we call them in Chapel, is where the map data structure is. And that's like a dictionary in Python. So next you see a couple of variable declarations. These variables are being declared as config const or configuration constants. These are a super cool part of Chapel. I started as the lead of the team in January 2021, but I was familiar with the Chapel programming language for many years before that. And I found this was really cool because it does command line parsing for you. And so when I declare something as a configuration constant in my program, then when I go to run the program, or even at compile time, I can specify on the command line what value I want that to be. All right. The next set of code is reading all the lines from an input file. So it's declaring a couple of string variables. It's then opening a file in read mode, creating a file reader called infile, and then calling the method readLine on that infile. And it will continue to do that. And then it's just concatenating up into a sequence all of our the sequence data that's spread out over lines in the input file. Next, we're declaring a variable in k-mer counts, and this is the type of that variable is going to be a map, and the key for that map is going to be of type string, and the value is going to be of type int. And so our map is a generic type, and so you can have maps of various types pointing to values of various types. And finally, we've got the code that's actually doing the k-mer counting. So a k-mer is some sequence, in this case, k equals 4. So it's going to be 4 characters. And we're trying to count up how many of each kind of 4 characters we're seeing. So this is just a serial for loop. And so we've got a for loop indexing into our sequence. So starting at the 0 and going all the way to before the end of the sequence size. But notice we're subtracting off that k because we want to look at substrings of size k. And then we're indexing into the map in k-mer counts with a substring from a sequence. So we've got the whole string sequence, and then we're indexing into it from the index that we're at, ... and then pound k indicates, hey, we want k characters in this range. And then we're just counting those up. So let's go to the next slide. This is talking about how to run the k-mer example. So in the top right, for this tutorial, we have a makefile set up, and you can just say make run k-mer, and I'm going to show you how to do that. There are other ways that you can run k-mer with different command line values for those configuration constants for k and for infile. And so you can see the slide also shows you how you would typically compile this with Chapel and then run it, and then different ways you can play around with it. All right. So let's stop that share and switch to the terminal. All right, let me make sure this guy's still alive. Okay, so I'm in that cuff 23 Chapel subdirectory. And I can see here, let's do a clear. There is that k-mer.chapel file. If I bring this up in Vim, see that we have some syntax highlighting for that. And so the name of the file it's going to bring in is k-mer large input.txt. So let's do a quick more on that. And so you can see that that is a sequence, genomic sequence on multiple lines. And so if we want to run this program, we say make run k-mer. And the make file is going to first call the Chapel compiler. The -- fast option is telling the compiler, go ahead and generate fast code. So do optimizations on the code. That's especially helpful if you're doing any kind of stream processing. All right. And as you can see, the output was some information about how many unique counter k-mers we have, 255. And then we also just did a write line on the dictionary or the map, and it's showing for each former the count for it. All right. So any questions at this point?
We do have a couple questions in Slack. So the first one is, what is the value returned from the map if the key is not present? So for example, the +=1 the first time the sequence is encountered.
So the +=1 is the first time the sequence is encountered. The default value, I believe, is 0. Yeah.
The next question in the chat is, exactly what optimizations does -- fast perform?
Exactly what optimizations. Wow, that's asking a lot of a tutorial presenter. There are lots of different things, but the key difference between when you normally compile Chapel and when you say -- fast is compile Chapel code normally is checking that you're not going over array bounds. So there's array bounds checking code in there. And there's some other safety code that's in there. And so the -- fash is going to take that away. And so that's one of the reasons why things are significantly faster. And there are lots of other optimizations as well. And we'd be happy to hear from you on Gitter or Discourse to ask the team. And there are some people on the team that can go on in quite length about all the different optimizations our compilers performing. Any other questions?
So there was also a question about where exactly this chapel code is running when you do make run on Perlmutter. And so I think the answer is we've said that the make run is actually just a very simple make file that tells Slurm to schedule nodes and run the job on the compute nodes. It's not the only possible way to run chapel, but it's the recommended way on Perlmutter, is that the computation should not be performed on the login nodes. So the login nodes are for compilation and the compute node should be used for computation. So that's what this make file currently does.
All right. Thank you for answering that one, Dan. I'm going to switch back to the slides.
Another question just popped up asking if the map implementation is a hash table or a binary tree.
Yes, hash table. Good question. All good questions. All right, so the key
Code
concepts.
creating new dictionary keys as it parses through the file.
Yeah, so every time it sees new substrings that you're passing into the map, then it's going to call hash on that. And so the Chapel compiler is like generating like default hash functions for the built-in types like string and integer, but also for some user-defined types. Most user-defined types, yeah. But any other questions?
We still have questions coming in. Do you want more questions? Yeah. So the next one is, can Chapel accommodate irregular data as mentioned in the UPC++ presentation, for example, graph computations? It
can. Yeah, because like UPC++ and Coarray Fortran, because we're PGAS, it's a little bit easier to deal with irregular data because you can just go ahead and access that data in that global address space, even if you're jumping around a bit. And then the runtime is going to do the necessary gets and puts for you. Now, this code, again, is serial. This little example here, I'm going to switch to parallelism next. So I'm actually going to go ahead and get started with that. All right. So let's talk about parallelism and locality in Chapel. So I brought this up in the 20-minute intro that there are lots of different kinds of parallelism in Chapel. I've got example syntax for most of those, but I've highlighted the ones we're going to be focusing on in this tutorial. So the for all and the for all. There's also some examples in the directory. There's one example that uses sinks, like that heat 1D task uses sinks. And there's the GPU code has like a cobn in it. And then there's also like a reduce in the heat diffusion codes. But we're really going to just be talking about the for all and the for alls during the tutorial. We're more than happy to answer more questions about these constructs in the Slack and also in general on the Chapel Discourse and Gitter. So we saw that slide with all the cool applications that are currently using Chapel. And here again are the links so that you can go find out more about them if you'd like. So I looked through many of these and tried to get an idea of what kinds of parallelism are the applications actually using. And so you can see that using for all for distributed parallelism and also for threaded parallelism is very common in many of the applications. There's a little bit of use of cobn, and we will see an example of that later on these slides. And then there's also usage of for all, because for all kind of takes advantage of distributed parallelism if you're iterating over a distributed data structure, and it also gets you that threaded parallelism on each locale. So we're going to focus on those yellow columns, highlighted yellow columns. Let's start with our parallel hello world. And you saw that in the 20-minute, just in case you didn't see the 20-minute, I'm going to go ahead, go back to the terminal. There's quite a few little hello examples like hello 6, taskbar, and hello disk node names, etc. You can try all of them. I'm going to just do the hello par one. So if I say make run hello par, you're not seeing the compilation command because it was already compiled. So it's just running it, and it's running it with one locale. There you go. And then this is the one that at the top, it does have a configuration constant to indicate the number of tasks. So we can run it. Let's try two locales and tasks per locale equal to 3. And then we'll get to see a little bit, we'll get to see both levels of parallelism across locales and within each locale. So there should be 6 messages coming out. I think this is the little bit of hesitation that we're seeing from the queue on Perlmutter. But there it goes. All right. Okay, any questions at this point?
I don't think so. We've been dealing with some tech support issues, but not about Chapel.
All right, great. All right. So you can see that the code in that hello world is these nested co-for-alls. You've got a co-for-all over the locales, and then for each locale, we're iterating over some number of tasks, and then we're printing that out. So let's look more, let's look conceptually at how things are working in Chapel. So here I've got 4 compute nodes, and they're connected with a network. In the light blue, you can see that we've got 4 processor cores on each compute node. And then the orange rectangle is representing the memory on the compute node. In Chapel, you have the concept of a locale. And a locale is a compute resource in your program that can have processors associated with it. So you can run tasks on those, and it gives you an abstraction for memory. You can store variables there. So for now, let's just think of each compute node as having one locale running on it. Okay, so now I've renamed my compute nodes locale 0 through locale 3. And we've got some key built-in variables for referring to locales in Chapel programs. You already saw these in the 20-minute intro. There's the capital locales array for all the locales. So if I say -nl space 4, then I'm going to have a locales array with 4 entries. And then here refers to the current locale. And somebody is asking, can a locale be an accelerator? Yes. Thank you, Jeremiah. We'll get to that. All right. So when you start a Chapel program, you're going to have your first task, your main is going to be running on locale 0. And you can see the little gear showing a task executing. When we have parallelism, one of the questions is figuring out like which tasks should be running at the same time. And so if you have 4 cores that locale has access to, you could have 4 tasks running at the same time. Then there's also the question of locality. Where should a task run and where should data be allocated? Okay. So if I have a task per locale, Then I've got distributed parallelism, and I've got a task running on each of these separate locales at the same time. I can also have, in addition to that, shared memory parallelism on each locale, where you're taking advantage of all the cores to execute multiple tasks on each locale at the same time. So now let's talk about data. So here I've got a little 2x2 array that's on locale 0. If I distribute that 2D array over these 4 locales, then I would have just one element of that array on each locale. Of course, you need to think beyond our little programs that we run in PowerPoint and think about, really large arrays, and you break up the array in about an even block per locale. Each locale can also have their own private arrays as well. So let's actually look at a Chapel program and in correspondence with this picture of what's going on. So we start every Chapel program. If you print out here.id, you're going to get the ID for locale 0, because everything starts in locale 0. Now we're declaring an array in this program, a 2x2 array. So you see that 2x2 array is allocated on locale 0, because that's where we're executing. And then we can use the on statement to allocate data and execute on a different locale. So if I say on locales 1, once I go inside that on compound statement, I'm going to have a task executing on locale 1. When I allocate the B array, that ends up on locale 1. And now when I do a computation that's going to read the A array, so it's going to read all the elements of the A array, multiply each element by 2, and then store the result in B. And so you get a remote access to A to do this computation, and then the result is stored locally in the B array. All right, any questions about this? All right, I'm going to keep going then. After we come out of the on locales 1 statement at the end of the right-handed curly brace, we are now back on locale 0 again. And so what you just saw is a serial computation, but it's distributed. So it executed first on locale 0 and then locale 1, and then went back to locale 0. So another way that you can execute serially across locales is with a for loop. So you can do a for loop over that locales array. And so in this for loop, I'm iterating serially over all the locales. And for each of those locales, I'm going to copy the array A into a local B array. And so locale 1, when it's executing that, it's going to create its own B array and copy A into it, locale 2, locale 3, etc. All right, and then at the end of that for loop, we're going to end up back on locale 0. So I see someone asking, is locale 0 is the default? Yeah, we start out in locale 0. Okay, and it's not until you use these on statements does where you're doing computation move. The way we typically do this is some kind of a for loop or a for all loop or a for all loop. You see here this for loop has got nested inside of it an on statement to say which locale to execute on. So this example is also serial, but we're doing a distributed computation. Now let's do some task parallelism, as well as distributed computation. Wait, mixing locality with task parallelism. I think my title is incorrect here, but okay. This co-for-all loop is going to create a parallel task per iteration. And since we're iterating over the locales, we're going to get a task on each locale. So we do have task parallelism here. It's just distributed task parallelism. And so now those copies of the array A, every single locale is copying that into their own local B at the same time. Then after we get out of the co-for-all loop, we are back to locale 0. Now let's look at array-based parallelism and locality. This is also referred to as data parallelism. So we've got our array A like before. Now we're going to declare the B array as block distributed. So what's going to happen is that B array is going to be distributed across all of the locales. Then when we do this array assignment, we set the array B equal to all the values in the array A. Underneath the hood, that's going to be implemented with a for all, and it's going to do that copy in parallel because the array B is distributed. Right. There's that copy happening in parallel. Okay, so we already ran this example. If you would like the parallel hello world example, if you'd like to try out, different numbers of locales I recommend that you keep to a small number of locales, maybe 2, 3, or 4. And then you can play around with the task per locale. And that you can get with bigger numbers if you'd like and see how that works. Okay. So to sum up, we've got parallelism and locality in Chapel, and there are really these orthogonal concepts. So here's an example where we've got parallelism, but it's all happening on one locale, whichever locale we're on. And so you've got that shared memory parallelism happening on a single locale. You can have a distributed program like this one, but it's serial. So you start out in locale 0, then you say, okay, now go on to locale 1 and do a write-len and output something, then go on to locale 2. And then you can even have nested on statements as well. So I can move the computation from locale 2 over to locale 0, and then we pop back out in the outermost scope. You're always in locale 0. And then you can also have distributed parallel programs so that you've got the parallelism and you've got the distributed data being distributed. And just the computation being distributed. So here, the co-for-all is going to do a parallel task per iteration. And because nested inside of that, you've got an on locales that's computing which locale to print this message out from. So you're going to have some of these messages are going to be being printed out from the different locales that you have available to you. All right. So any questions on this before I go on to the parallel file processing example? Okay. Just to give people an idea, we're about 30 minutes in, so we're about a third way through the tutorial for Chapel. So next up, we're going to be looking at how to process files in parallel. The example for this is the par file k-mer.chapel. So let's actually go give that a try. I do encourage you to go ahead and at least try to compile and run while you've got helpers in Slack, that if you run into any snags, we'd really like to help you get to the point where you can compile and run these code examples from all 3 programming models. So please do ask questions, give it a try, and if you get stuck, please do ask questions. Okay, so we're going to do a make run par file k-mer. That's going to compile the Chapel program. And then it's going to run it. All right. So let's go look at this code in PowerPoint and see what it does, unless there's any questions.
There's actually one really interesting question, which is, what is the recommended way to profile Chapel programs?
The recommended way to profile Chapel programs. There's a lot of putting timers in there that I see the team doing. But actually, yeah, this might be a better one for Jeremiah to answer. I've also, Brad worked with some of the folks. Oh, that was with the debugger. So it's actually a good question. I don't know the answer to. So
I was also going to say the comm diagnostic stuff, Michelle. I'll paste some documentation links into the Slack chat.
Yeah, thank you for reminding me about that. Yeah, there is a communication, it's called comm diagnostics module, where you can put in calls to that to get an idea of how many remote puts and gets were happening in your program to help you figure out what's going on there. And Jeremiah is going to put links to that. And I recall that Jeremiah has some calls to that in some of the heat diffusion codes. He wrote most of those heat diffusion codes. All right. So here we've got the par file k-mer code, and it is using a for all for the parallelism. So what it's doing is it's saying, all right, I'm going to use file. It's using the file system module, and it's declaring a configuration const data dir. And then it is saying, I'm going to get a list of files by calling find files. So that file system module has defined that function find files. And it's going to give us a list of strings of all the file names in a directory. So then what we're doing is we're actually creating an array using the block distribution. We're creating an array of size, the number of files we have, and of strings. And because we're doing it with the block distribution, that array is going to be distributed across all the locales that we have available to us. And then we're initializing that array file names with the list of files that we have. So now when we do this for all over all of the files in the file name, since it is distributed, you're going to get parallelism across all the locales available. And for all is also going to take advantage of the parallelism available within each locale. So if you only had one locale, you would still get parallelism with this approach because you're going to, because you're using that for all. And so it's going to essentially do that k-mer, that serial k-mer computation on each file in parallel. Okay, and this can be really handy when you've got lots and lots of files to analyze, and you want that the analysis of different files can be done in parallel. Okay. So are there any questions on this?
So I have a question.
Yeah.
Maybe I missed it, but so there's no on statement in the code on the screen here. So what causes it to run on multiple locales?
Very good question. The for all is using the default iterator that's associated with the file names array. So all of our distributed data structures and really all of our data structures have these default iterators associated with them. And that default iterator, which is just implemented as code, and users can write their own iterators. That iterator for distributed arrays is going to use a co for all and then an on loc for the outer loop. So it's going to use two co for alls. That co for all over all the locales and use an on statement, and then a co for all within each locale to take advantage of the parallelism there.
So there's a related question in Slack, which is what if you had written co for all instead of for all here in this code?
That's also a very good question. So if you write co for all, just replace that for all with co for all, you're not going to get distributed parallelism. And that is because I don't have an on statement in here. Okay. The co for all is lower level semantics, if you will. Co for all is always going to create one task per iteration. So you're going to get one task per file. And you're only going to get that parallelism across locales if you then have, if you're iterating over the locales themselves. Okay, so the for all is very convenient in that the default iterators are gonna, for distributed data structure, they're gonna break things up. You know, they're gonna iterate over the locales, and then within each locale, they're gonna break up the computation evenly across the cores available. Any other questions? Okay, great. So this is just giving you a bit of a visual of what that distribution might look like of that array if we had two locales and we had 8 file names. So if we had 2 locales, that array of size 8 is just going to be split into 2. Locale 0 is going to have the first 4 entries, and locale 1 is going to have the other 4 entries. And then if we call that par file k-mer with 2 locales, that for all is going to give you parallelism across the locales, just as I mentioned before, and within the locale as well. All right, so I recommend that you play around with this example program. You can specify a different directory, and what the program does is it's just going to process all the files that are in that directory. And so you can put lots of different files in there. You can specify different values of k. And so we did talk a lot about the for all loop construct in this example, but we're not really seeing puts and gets happening yet, because the way these files are being processed is you're just processing, each locale is processing its own set of file names essentially, and has its own map. So we don't have any puts and gets happening. So that we'll get to next. All right. Okay, so I do see a question in chat. Can Chapel run bare metal, or do you absolutely need OS support? Well, anything running on bare metal does need OS support. So I'm not quite sure what that question, maybe we can get some clarification to that in Slack or something. Do keep the questions coming though. All right, I'm going to move on to the heat diffusion problem that we initially talked about. Okay, so the heat diffusion problem is an example where we're going to need puts and gets. So let's talk a little bit about when are puts and gets going to happen in Chapel. So as we've discussed before, Chapel supports a global namespace. So you start out in locale 0, and variables are allocated on the locale where the task is running. So in this example, I've got 3 variables. I've got verbose, total, and done. And you can see on the right, they've all been allocated on locale 0. If I go into an on block where I want to start my execution on locale 1, and I declare some variables there, those variables X, Y, and Z are going to be allocated on locale 1. Now, this is all true, but we have this global namespace. And so in locale 1, if I do computation, so instead of declaring variables X, Y, and Z, if instead I do a computation that refers to the variables done, verbose, and total, then that computation is going to happen on locale 1. But that computation can see lexically in that program, based on scoping, that computation can see those variables. And so it can refer to those variables. And if necessary, puts and gets are going to occur to make that happen.
So there's a question in Slack. How will array splitting and parallelization behave with arrays with odd number of elements?
It does work. I just don't know exactly how. I don't know the gory details of that. Jeremiah, do you happen to know that answer to that question?
Yeah, with the block distribution, the remainder will just get spread evenly across locales. So if you have like 10 locales and 101 element array, then one of the locales will get the extra element. It'll have 11, and then the other 9 will have 10. I'll send some docs for that though.
That'd be great. Thank you. Any other questions?
Not currently, and we're at about the halfway point of this session.
Yep. Okay. We're good. We're in good shape in terms of time. All right. So now let's go look at these heat 2D codes. Look at running them.
There's another question. Will the total on locale 0 change after running on 1?
Yes,
Exactly
yes,
what they're
because
okay.
that total variable is globally visible to everybody that can see it in terms of scoping. And so as long as you're in a part of the code that can see that variable in terms of scoping, then they'll be able to see that change.
So it's a really great question in Slack. I love this question. Is accessing the verbose variable that lives on locale 0 causing network access when it's accessed from locale 1?
So that is a great question. And that is going to depend. So in that particular example, let me just switch back to it. So I'm not talking about something that y'all are not looking at. Oh, what happened? There we go. So notice that verbose happens to be a configuration constant. So at the beginning of runtime, whatever value verbose is going to have is locked in, right? It's going to be constant. And so the Chapel compiler knows about that kind of thing, so it can optimize for that kind of thing. So verbose will not need this if verbose is not going to have to generate a get because we know what that is. Chapel's also able to do that with constants like this total. If nobody else is, I'm sorry, like done is a constant and isn't being modified, but total is being modified. And so total, there will have to be gets and puts to the total variable. So that's a great question.
There's another question, which is, are the operations on global scope variables atomic?
Only if you make them so. Yeah. So you can declare atomic variables and sync variables in Chapel. And Jeremiah, could you put some links to information about those kinds of variables
I think you
in
just
the
yes. Yeah.
chat? Thank you. Or the Slack. Any other great questions while I'm on the slide?
There's a lot of great audience involvement. I see many people typing. So, oh, here's another one. How are locales distributed across multiple nodes? Does Chapel use topological information of a cluster?
Okay. So locales are evenly distributed across the nodes. We do have, and typically it's one locale per node. We do have functionality in our newest versions of Chapel that enable you to indicate at runtime that you want to run multiple locales per node. So for example, maybe you want to run a locale per socket so that you get to take advantage of NUMA affinity. There's also functionality of a locales per NIC. I'm not sure that's in the last release. That may be in this upcoming September release. I believe that's like really cutting edge stuff that's coming out of the team. So then the other question was, there was a second part to that question.
Okay.
What was it? Can you remind me?
Do you use topological information of a cluster for placement of locales? I guess they're asking.
Yes, yes. So the runtime is using HWLock, the HWLock library.
Okay. The next question is kind of an open-ended one, which is how would a locale access another locale scoped variable or data? I think this is kind of handled or explained already, but
yeah, but I think this is, this is a tough concept to kind of understand. It's when we're all kind of familiar with the scoping rules within a program. And so, if I'm just looking at this as a serial program, verbose, total, and done are allocated, if you will, at like a kind of a global scope or a module scope, whatever you want to think of, or function. If we're inside of a function, they're allocated. And then inside a block, inside the on block, let's not think of it as an on block. Let's just think of it as like just curly braces, right? Inside that, I'm going to be able to see things that are in the outer scope. And so if that's the case, if you happen to be on a different locale in Chapel, you can still get to those variables as long as you can see them in terms of lexical scoping rules.
So there's another question that's not really related to the code on the slide, but are arrays of bools in Chapel implemented as bit sets or arrays of chars, byte-like?
I don't know the answer to that question. Jeremiah, do you?
I do not. I'm gonna look it up real quick though.
Okay, Jeremiah's going to look that up for us. All right. Any others, or should we go look at code?
Actually, this is a really good question. Does Chapel have a preprocessor equivalent?
It does not. But what we do have, which isn't a preprocessor, so it's different, but there are param variables.
You have template-like generics, right?
Yeah, and so, well, yeah, so we have generics, but then there's also these param variables that are essentially compile time constants. And so we have a certain amount of compile time substitution, and I think we're looking into potentially doing compile time unrolling if you have a for loop over a param variable. So we have some of that, but we don't have a preprocessor. It's a good question.
This audience involvement is great, but I think we should probably push on with the presentation.
Yeah, I'll get going. Let's now start running the program. Let's clear this up. So let's look at all the heat 2D variants. There's quite a few available. We're going to be looking on, just so happens, the three on the left-hand side, the heat 2D chapel, the heat 2D dist buffers, and the heat 2D dist. And so, like with everything else, you can say make run heat to the name of the program. And now it's going to compile and run it. The heat 2D one is going to give you shared memory parallelism, but it's just going to stay on one locale. All right. The heat 2D dist is the next one in the progression, not alphabetically, but it's the next one in the progression. And that is making that simple change I showed in the 20-minute, and I'll show it again, I think. Yeah. Where it's now distributing the array, so you get both distributed memory parallelism and shared memory parallelism. You can see the output of these is showing the mean and standard deviation of the values and then the time. So in the README, in this chapel subdirectory, there's a little shell script command that you could use to try out different sizes to see what kind of scaling you're gonna opportunities there are for some of these codes.
I think it's also worth mentioning that when we're using this make tool to automate the compiler and run steps, but they're also printed on the screen as they're happening. So you can, if you feel like fiddling with the arguments, you can copy and paste those commands and change them however you wish and experiment around with things.
Exactly. So for example, I'm going to try the heat 2D dist with 2 locales, because I don't know if you see this here, but we actually got 10 times slower with the when we did the distributed version. And so this speeds us up a little bit. If you would really want to see the advantage of the distributed memory, then you'd have to use a much larger problem than what we're using. Okay. And then we'll go ahead and do the make run heat to the disk buffers. This has got an optimization that Jeremiah has put in. Jeremiah wrote all of the heat distribution codes. And is one of the developers on the chapel team. Waiting for compilers. All right.
I believe this dist buffers version is the one most similar to the UPC++ and Fortran versions that we'll see, well, that we saw briefly earlier today, and we'll see again.
It is, and you'll notice that it's faster than the heat 2D dist. And we'll look at some pictures and get a little bit of an idea of why that's the case. Uh-oh, Brad's got an XKCD. I'm not going to look. But I'm guessing it's about waiting for computers to do stuff. Now we're waiting for the queue. We're not waiting for the compiler, we're waiting for the queue. And okay, great. Going to 2 locales slowed it down. No, it's not wonderful. But okay. So we could play around, and you can feel free to play around while I'm talking, but I'm going to go ahead and go back to the slides.
But I think the experience you just had is a fairly common one, which is going from one compute node to multiple compute nodes is always gets slower, but then going to more than 2 gets better. So
yeah, and it also has to do with, you know, problem size and how long are you waiting for the queue, and there's lots of things that go into it. All right. So remember when we were talking about, we had this example of creating a block distributed array. So the array B here has been distributed in blocks across all the locales in a two-dimensional way. And then the computation done on B is now going to be a distributed parallel computation because of the default iterators associated with arrays. Well, we're taking advantage of that in this implementation of the parallel heat diffusion. So the initial version, as I said before, has the old time step UN and then the new time step UN plus 1, which is stored in U. And the for all loop within each time step, we have a for all loop over all the spatial coordinates, the inner spatial coordinates, where we're in parallel calculating those new values. Well, when those arrays are distributed, like they are in the heat underscore 2D underscore dist, then that for all loop, that same for all loop is now going to get the distributed memory parallelism across the different locales and then still get the parallelism within a locale. And the puts in what we're getting from being a PGAS programming model here is that we don't have to explicitly send and receive the values they're coming from the different locales. But if you do have if you're accessing a value that is in a different locale, there's going to be a get that has to happen to make this computation happen. So in that heat 2D underscore dist, it's just kind of naively, it looks very similar to the original code that's not using distributed parallelism. And it's just going to do gets whenever it needs to. Now to optimize that, we can do management of our halos and what values are being sent. We can do a little bit of management there, and it's going to make things much more efficient because those gets and puts will be like aggregated together and they'll happen kind of all at once. So I've taken one of those subdomains and kind of shown you where it is down below. And now every little subdomain, we're going to have a north, south, east, and west. I'm only showing the west and the north in this example, little buffer to store information in. And so what the computation does in that code, that dist buffers code, is it's going to copy those edge values from the neighboring domains into the neighboring domains are going to copy their edge values into their neighbor's halo. Then each locale is going to copy all of its halos into its own local expanded view of their subdomain, of their own subdomain. So it's going to copy into the local halo. And then each locale is going to do its own computation in parallel. All right. But this does reduce the amount of communication that's happening between nodes somewhat and kind of aggregates that communication. So are there any questions on this one?
I'm not seeing any currently.
Okay. All right, so now we're about 2/3. We're about an hour in, about 2/3 done. We got about another half an hour. All right, so actually, let's look at this, some snippets out of that heat 2D underscore buffers code. So first you can see some code that is declaring and distributing the U array. You've got those indices, our number of X and number of Y. So a two-dimensional domain called indices. We want an indices inner, which is those inner values, because those are the ones we're going to compute over. And so we can take our indices domain and we can expand it by -1 to kind of shrink it by 1. And then we have indices inner. And then the all capitals indices is going to be a distributed domain that block.create domain gives to us. And then when we declare our U array, we're going to use that block distributed domain. We get our UN just by essentially copying, initializing it with a copy of the U array, and it will have the same distribution. All right. For the halos, we're actually using that block distribution module again to create a domain. And we're asking it to create a domain that is the size of the number of locales, our target locales. Okay. So if we have 4, for example, then this domain is going to have essentially one block per locale. And so our halo arrays is a 2-dimensional array. Well, it's actually an array of arrays. So it's a distributed array that's distributed 1 per locale. And then on each locale, it's going to have 4 halos. So north, south, east, west. And then we're just using these param values, that these are compile time constants, to index into that inner array. So
Does it
now
create
in
an
our
interesting
go-
question in chat, sorry, to ask, how in Chapel, how hard is it to go from 2D to 3D solvers?
in Chapel, how hard is it to go from 2D to 3D solvers? So let's see. So your Chapel has multidimensional arrays. And so you would have to make these indices. You could add a comma 0 to NZ. And the block distribution can handle multidimensional array distributions. So not too difficult because of the fact that we have the multidimensional arrays.
There's another question, which is, are there libraries or packages for common Chapel functionalities?
Yes. Yeah, so there's a bunch of standard libraries, but then there's also some libraries in the subdirectory called packages. There's like a linear algebra package. I think one of the standard libraries actually does regular expressions. I don't know many off the top of my head, so I would recommend looking those up, or maybe asking on Slack for particular ones, and Jeremiah can help you find what you're looking for, or let you know if there's an opportunity for you to add a library to our packages.
And speaking of that, I think you're also going to provide pointers to Chapel community resources for people after the tutorial.
Yeah, at the end of the tutorial, yeah, some of the last slides has a lot of URLs and pointers to how you can participate in the Chapel community. All right. Okay, so now let's go ahead and look inside the time loop. So the time loop is a serial loop. 4, 1 goes to number of time steps, NT. And toward the beginning of that loop, you can see that each locale is going to take some of its values from ulocale2. So ulocale2 is one of the local arrays that each locale has their own private copy of. And so it's going to take one whole side of that, like its west side of that. The ... is getting like a whole range of values there. It's like all available things on that west side. And it's going to copy that into its neighbors halo array, east halo array. And so TIDX is okay, this neighbor has the same task ID on the X direction is me, but it's going to be the task ID Y -1. So that's my neighbor to my left. And I'm going to copy into their east halo. Okay. Then there's a barrier because we have to wait for we have to make sure all the locales have finished copying into their neighbors' halos before we continue. All right. And then there's an array swap. Locally, the U locale 1 is swapped with U locale 2. This is just a reference swap. It's very fast. And then each locale is essentially going to copy from the halo arrays into its local array and then do the computation as usual. All right. I did mention the barriers. There is a way to declare barriers. I haven't shown the declaration on this slide. However, it is in the code, in the example code, and then you can call barriers over that barrier variable B, and that's going to be a barrier over all the locales. Any questions at this point?
There's a general question about interoperability, which is, can you mix the programming languages like running C or Fortran code inside a Chapel program?
Yeah, you can. We do. We definitely have people calling C code from Chapel. So Scott Bachman was a visiting scholar with us for the past 9 months. He's a scientist at NCAR, so National Center of Atmospheric Research. And so some of the codes we have are codes that he has developed. And his coral reef code, not the example code I'm showing to you all, that's for testing purposes, but the full one that he is using, he and his collaborators use all the time. He's using the lib PNG to read in PNG files. And then we have other examples in our CUDA. There's some functionality that reads and writes Parquet files. And so that we're making calls into. I believe that there we're calling into the C++ Parquet library, if I recall. But the C interoperability is quite good. Any other questions?
No, I think we should push on.
Yep. All right, so that's the heat diffusion example. Here are the 3 that we focused on in terms of looking at, what they're doing. There's some 1D versions in there. There's a heat 1D task version that's using some sync variables. And so you may want to check that out if there were some questions about test parallelism. So you may want to check that one out if you're interested in that. All right. So now let's move on to the image processing example. I'm going to try to do this one in about 5 minutes so that we have enough time to talk about the GPU stuff. Okay, so the image processing example, I'm showing you here in this slide how to run it. This one is not set up to run with the makefile, so you need to CD into the image analysis subdirectory. Look at the README. The information is also on this slide. Okay, but first let me talk a little bit about what it's doing. So this is a code that Scott Bachman wrote in Chapel. And the problem that he and his collaborators are looking at is ways of looking at satellite imagery of coral reefs and trying to determine where in the coral reef is there the most diversity, because then you can prioritize where to, in terms of policy, how to try to improve things and save the most diverse parts of the coral reefs. The computation that's being done is doing this very large neighborhood convolution over the image. You're masking out the land, you're only doing it on the water parts of it. And so you think of this little mask going over the whole thing. And that's the computation. So Scott started with us in September of 2022. And that's when he started learning Chapel. He did not know Chapel before that. He started the Coral Reef application itself in December of 2022. He started writing it. And he already had collaborators presenting results from the output of this program in February of 2023. And so it was a very quick development time in terms of him learning how to run in Chapel. Of course, he was able to ask questions of the team, and he did. We're more than happy to help answer questions on Discourse and Gitter for people who start developing in Chapel. So feel free to ask us for help. And then, oh, it wasn't last week. I should have updated this. And then about a month or so ago, Scott started working with our GPU support team. They changed about 5 lines of code, and they were able to run some of this on the GPU. There is a version of this Coral Reef analysis code where Scott and his collaborators are trying a more precise algorithm for figuring out the diversity. And it actually, it takes just hours and hours and hours. It's because it's got a O of n squared complexity at each point. So you essentially have an O of n cubed computation. So it just isn't working for the large images that they're now able to analyze. And so that's the one that they're porting to the GPU right now. So this application is less than 300 lines of Chapel code, and Scott has been running it, scaling out to hundreds of processors on Cheyenne, which is a machine that NCAR has in Cheyenne, Wyoming. And the full map for this version is able to be calculated in seconds rather than days. They used to have a MATLAB program that did this. And this, it wasn't all Chapel. Some of this was algorithmic improvements. So the way that Scott's doing the parallelism in this code is he's taking that 2-dimensional image domain and he is distributing it across the locales with swaths of it. Because part of the algorithm that he is running is taking advantage of nearby convolution squares share some of the results from the previous ones. And so he's only computing the new results. So that's the big algorithmic change that's helping quite a bit. And so then he gets parallelism across locales. And then within each mask, he gets shared memory parallelism. All right. So if you go look at Scott's example, you're going to see an example of user-defined modules. So he's actually created some of his own modules, and then he's using them in the main.chapel file. You can see that he's reading in a single file in parallel. And so this is slightly different than the processing multiple files in parallel. So the example I showed you before, you've got a whole directory full of files, and in parallel, you're processing different files. This is reading a very large file, having multiple tasks read parts of that file at the same time. And so that can also be helpful if you have large files. He's using sparse domains to create masks, to mask out the land. And he's got that 1D distribution, and he's doing that by reshaping the locales array. And he's also getting, you'll see in that code that there is some smaller arrays that are just stored on locale 0. So some gets are going to occur. Everything else is local, but there will be some gets to some of the smaller arrays that only live on locale 0. All right, so let's talk GPU support. But first, any questions about the image processing example?
Not that I've seen. This is a really cool application. I enjoyed reading the Chu paper about this. It has some definite real world impact on biodiversity and climate change.
Mm-hmm.
It is very relevant. So it's cool to see this working.
It's so much fun. And Brad and I got to meet with some of Scott's collaborators who are trying, out new algorithms on this, and they want to use it for more policy work and stuff like that. So it's really fun. All right. Okay, so let's talk GPU support in Chapel. So there's, we've got kind of two main ways to support GPU computations in Chapel. One is from Chapel code, generating code for the GPUs. And so for that, we have support for NVIDIA and AMD GPUs right now. We are exploring support for the Intel GPUs. And then there's the other approach is you can have Chapel code using the C interoperability, calling CUDA examples. And I actually have some links there where you can go see code that is doing that. Where you have Chapel code calling into some CUDA examples. Of course, we could also call into HIP examples because we're just using C interoperability. It's not special to CUDA. All right. And so the key concepts here is we have this locale concept, and we've expanded that concept to have sublocales to represent the GPUs. Okay. And the for all and for each, we haven't talked about for each loops, but the for all and the for each loops can be converted into kernels that are then launched onto the GPU. And the locale concept is still in play in that if you declare an array inside of a GPU sublocale block, then that array is going to be allocated on the GPU. So oh, and I strongly recommend you go to the tech note about the GPUs. It has a whole bunch of extra information. The URL is at the bottom, and it has lots of examples of using our GPU support. I'm going to show you about 4 or 5 slides with GPU support here. So on the right, we see the GPU example.chapel. It is a code that is in your in the tarball. You're not going to be able to run it on GPU because we don't have a GPU allocation on Perlmutter, and the AWS instance is not a GPU allocation. But it will compile and run. It'll just compile and run on CPUs. Okay. So in this example, we've got a GPU diagnostics module, and that is, we make a call to start GPU diagnostics. This is super helpful because it will kind of let you know like when kernels have launched, etc. It's kind of like COM diagnostics, which is letting you know when are the puts and gets happening. This is another way, GPU diagnostics is another way to have an idea of like what's happening when I run this code. Then the code declares a var operate on, a variable operate on. And that variable's value is either going to be a list of, it's going to be the array of GPUs sublocales, if there's at least one, right? So I'm asking on this locale here, is my GPU's array greater than 0, size greater than 0? If it is, then I'm going to set operate on to be an array of those GPU sublocales. Otherwise, I'm just going to make an array with my own locale in it. So then all of the code that comes after that is just using that operate on array of locales, whether they're GPU sublocales or whether they are, just the locale, just an array with one locale. That for all is still going to work. And it will iterate over the sublocales, and then the for each will be the kernel that gets started on GPU if you're set up to run on the GPU. All right. So let's look at some more examples there, examples of this. So this is an example where we're going to be running on the GPUs and the CPUs. Okay, so this example here is basically like, if I have GPUs, I'm going to run on the GPUs. Otherwise, I'll just run on the CPU. The example on slide 60 is I'm going to run on all my GPUs and all my CPUs. So you got all kinds of parallelism in this one. So the co begin, so first we have the co for all over all our locales. So that's going to go over all the locales that we have. Then you have a co begin statement, and co begin is going to create a task per child statement. We have two child statements inside this co begin. We have the co for all loop, and then we have just an unnamed code block that's happening. In the co for all, the co for all is going to, it's iterating over the GPU sublocales. So it's going to create one task per GPU, right? And then on each GPU, it's going to do this triad. So what is the triad? It's this computation that we're doing here. It's the stream triad computation. We're saying, take the vector B, add it to the vector C times alpha, and put all the results into the vector A. And then this unnamed code block is just going to do that vector, that array computation, you taking advantage of the multi-core on the CPU so that you're running on everything. All right. So do we have any questions about the GPU support at this point?
I see some people typing, but not yet. Oh, there's one. Is there a way to refer to or allocate memory on the different kinds of GPU memory, global versus shared?
That is a great question. So there's I think there is. I'm not. I think it's being done now with C interoperability. This would be a question for the GPU subteam. Jeremiah, did you happen to know, or can you like go ask?
Yeah, I can go ask for more details. I think there are multiple different memory modes that you can put Chapel in when you're compiling for GPU.
Mm-hmm.
One of them uses shared memory. And then
well, one of them uses unified, right? One of
unified,
them
that's what
unified, right.
Yeah. I can get the details on those environment variables and put them in the chat.
I know Andy did an example where he was allocating some of the data on the shared memory on the GPU. And so, yeah, pinging Andy and seeing if any of those are public examples would be great.
Sounds good.
There's another really great question here, which is, can variables on GPUs be remotely accessed by other locales?
That is a great question. Can variables allocated on GPUs be remotely accessed from other locales? I think that if it's a CPU locale, the answer to that is yes. But if it's a GPU sublocale, we do not have gets inputs between GPUs, or essentially GPU initiated gets inputs are not, we don't have that functionality yet. We are working to get that functionality, but I think everything right now is CPU initialized. So if it's a CPU locale that's trying to access another one, but I'm not, for my confidence on that one is about 50%. So we'll try to get back to you on that one. Let me jot that down.
And there's a question here about NCCL, which is the NVIDIA collective communications library, and whether Chapel supports GPU collectives using that or any other way.
So you could call into their library using the C interoperability. We don't have any collective support written in Chapel yet.
Okay, I think let's push on.
Okay, let's push on. All right, so let me show you some performance results that we have. So we have CUDA versions of the stream triad benchmark, and we also have HIP versions of it. And so on the left, you're seeing higher is better. You're seeing a comparison of C plus CUDA and Chapel. And with really small arrays in the stream benchmark, there's a little bit of a gap where Chapel is a little bit slower than C plus CUDA. But for larger arrays, we have the same performance. The chapel has the same performance. And then on the right-hand side, you can see with A and D that we're able to match the performance for the reference there. Okay, and this is as of our last release, which was just this past June. So the 1.31 release.
Got about 5 minutes left in our schedule, but we can go over a little bit, I think.
Perfect. I think we're going to be pretty close. But yeah, then we can take questions for a while after if people want to. Okay, so now let's go back to the model in Chapel of where do things run and when do things run in parallel and where is data. And we have to we've looked at this model of locales and how are we going to extend it with GPUs. So what we've done is we've decided to have this sublocales, so another level of locales. So you can have these locales, and within a locale, you can have as many GPU locales, sublocales as you have. And so you can kind of see what this looks like pictorially. And right now, pretty much it's got to be like a homogeneous, same number of GPUs per locale, that kind of thing. We're looking at expanding that functionality if we come across cases where we need that, but that's what we've got so far. And each of these GPU sublocales, they have their own processing units and they have their own memory space. Okay, so now you can kind of see like, all right, here is the stream code that are CPU only. You can either use the array arithmetic to get all the parallelism because the arrays are block distributed, or you can be more explicitly put in the parallelism as a code for all over locales and then do some array parallelism on each locale. Or you can do GPUs only. So iterate over all the locales and do a code for all over all the GPUs on that locale, and then do the vector computations. It'll take it, that'll be a kernel. This is a GPU only program. Or you can do the code again, which we saw before, and take advantage of all the GPUs and all of the CPU cores. Okay, so there are a lot more Chapel examples and presentations. Here are some links to get you started. There's some cool blog posts that have started in the team. Jeremiah is one of the contributors to some of the blog posts, so you can check those out. They talk through some detailed examples of code. And what I hope you're taking away from the tutorial is that it's a PGAS programming language. Chapel is a PGAS programming language. It's designed to leverage parallelism. It's being used in some large production codes. Our team is actually quite responsive to user questions, and we'd enjoy having you participate in our community. So please feel free to contact us on Discord, Gitter, or Stack Overflow. Also, feel free to email me at michelle.strout@hpe.com. But you're probably going to get more responsiveness from the rest of the team. But feel free to email me, and I will find out who can help you. And then you can engage with the community by sharing your sample codes, asking us questions. And then every year in June, we have a free virtual workshop that people can join. Here's more resources. And then here's the most important slide. I probably should have put it at the very front. This is the current Chapel team. We have a couple of interns on the far right, Ian and Nikki, with us this summer. And then everybody else on here is our full-time people working on the Chapel team, ordered by first name, alphabetically by first name. So, do we have any other questions?
I think let's all use the reaction button to thank the speaker. There's a clap button you can click and thank the speaker for her time and all her effort. She's put in a lot of work putting this together, both between the examples, which Jeremiah did a lot on, and
Yeah.
obviously the slides. And I think this was a great presentation. So thank you very much, Michelle. And I
Thank you,
just want
Dan and Paul,
to note
for all your help.
that although this session will be ending soon, we have a session tomorrow that starts in this same Zoom room. It'll start at noon Eastern, 9 a.m. Pacific. And so tomorrow the agenda is we're gonna have two 90-minute sessions. The first one will be, Amr will be presenting in more depth about UPC++. And then later on in the afternoon at 1:45, Damien Roussan will be presenting about Fortran co-arrays. So I strongly encourage you all to definitely come back for those sessions. In terms of what happens between now and then, I believe that the Frontier and Perlmutter reservations are ending soon, which means that some of your run commands might not work anymore overnight, but it'll be open again tomorrow during tomorrow's session. AWS will also be turned off at some point tonight. I don't know exactly when, but yeah, you shouldn't lose access to the login nodes of Perlmutter. So if you have a Perlmutter training account, you can still remain logged in and play around with the compilers. And oh, okay, apparently the Frontier reservation is on all night, Suzanne says.
Right, and the AWS and Perlmutter are due to end in approximately an hour. So at 15 after whatever the next hour is in your time zone.
Okay, but I definitely encourage you all to come back tomorrow and use the supercomputers tomorrow as well. And of course, listen to the wonderful presentations that they've prepared for us. And so with that, I think we can use the next 10 or 15 minutes to answer questions for Michelle or for the other two presenters, although just keep in mind that a lot of the UPC++ Fortran content is still to come. So some of the answers might be, you'll see about that tomorrow. But let's see. I don't see any Chapel specific questions at the moment, but feel free to type in the Chapel channel. I do see a question about UPC++. It says for the UPC++ library, it seems you can bypass the NIC for global RMA. Is there any particular hardware required for that? I think, Paul, you've started to answer that already. You want to go ahead and give the answer in Zoom here?
Sure, sorry, I'm fiddling with mute buttons here. So if I'm understanding the question correctly, what you're referring to is we use OS mechanisms such as POSIX shared memory to cross map the address spaces. So no special hardware is needed. Multiple processes running on the same compute node or host will be able to access each other's memory, the shared variables directly without specialized support, without any NIC, in fact.
Okay. Are there other questions or discussion topics? I love how many questions we've gotten throughout this whole session. It's really been great to have so much interaction.
Yeah, we really should thank all of you who have come and participated. This is a really great group, and thank you for all the questions.
Yeah, absolutely. Thank you, everyone. All right, I see a question in the Chapel channel, which is, are there more fine-grained sync primitives than barriers? Ooh, that's a good question.
Yes, there are. So there are atomic variables and there are sync variables. And I believe that Jeremiah may have put some information in the Slack, or was it going to try to? Jeremiah,
Yeah, that was further up in another thread, but I'll just paste it again at the bottom.
Appreciate that. There's definitely that finer grain synchronization that is available in Chapel, because one of the goals of Chapel is to provide pretty much like all different kinds of parallelism that you can think of. From when I've been looking at the different applications written in Chapel and what they're using, there's not a lot of that being used. So the co for all and the for all and co begin, those are kind of the most commonly used ones in a lot of these applications.
So here's a good question. In the heat equation solver, the memory was divided into squares, so 2D distribution, whereas in Coral, it was in stripes. What determined the difference?
Okay. Well, I'm actually going to show you code to answer that one. Because that's a really fantastic question. So let me bring up my terminal. All right. All right. So if I go into the image analysis subdirectory here, and we've got all the files in here, let's look in main. Here, main.chapel. And we have syntax highlighting because Dan went and got our Vim RC file for that, or the Vim syntax highlighting. Thank you for that. All right. So what I'm looking for is essentially there's a place in the code where Scott is taking the locales array, which is just a one-dimensional array, and reshaping it to be a two-dimensional array. Okay. And so that way, when the domain decomposition is done over a 2D array, it ends up being a 1D distribution. So I'll show you how that works. I just have to find it.
Line 150, Michelle.
Thank you very much. I have such an awesome team. Jeremiah, you're fantastic. Thank you. All right. Okay. So remember this built-in locales array. That's a one-dimensional array of all the locales available to the program. Well, when you do a block distribution over an array, that is going to make the distribution match the dimensionality of the array. And an image is a 2D array. So the distribution would be 2D. But Scott wanted a 1D distribution. So what he did is he reshaped the locales array from a 1D array into a 2D array. And that 2D array has all the locales in one dimension. And then that second dimension is just of size 1. Okay, so it just has one locale. So it's essentially saying, here's a domain, it is 2D, it's a 2D domain, but I've essentially made it a 1D array that's acting like a 2D domain. And then so when block does its distribution, it's just going to do that. It thinks it's doing a 2D distribution, but because one of the extents is only of size 1, it's essentially just doing a 1D distribution.
And there's a really good paper about this code, by the way, in June 23. I just dropped a link in the chat there. So if the question was, why did they do this? I think the answer is algorithmic. And so
Yes.
The paper lays out the reason why it actually makes sense to do a 1D distribution for this particular algorithm. It saves orders of magnitudes in terms of computation. So.
All right, I'll go back to the schedule.
Not seeing any other questions popping up.
I see one in chat. Does the Chapel user group or CHU event have any sort of an email announcement list so that I can find out about upcoming CHU events and other announcement events? I would have loved to have attended CHU this year, but I didn't know it was happening. So we do announce on our Discords, and we announced HPC announce. So Daniel Keller, I don't know if you're signed up for HPC announce, but I would recommend maybe you do that. Yeah, you can look at the events link, or you can send us email and I will try to get you on the list of people that we send out email to.
So speaking of events, there's an interesting upcoming event, which is PAW-ATM 23.
Yes.
So that events page is actually incorrect. The submission deadline has been pushed back to Monday. So this coming Monday, the 31st, is the submission deadline for papers for PAW-ATM, which is the Parallel Applications Workshop Alternatives to MPI workshop that's held at SC23 in November. And it is very centered on alternative programming models, which include all 3 of the ones that we're talking about in this tutorial. So there's typically at least one paper about Chapel, hopefully a paper about UPC++, sometimes a paper about Coarray Fortran. So this is one of the main venues of the year for research papers in these types of programming models. So if you're doing work here in these types of models, PolyTM is a great place to write a paper for, an abstract for, to propose a talk. And if you're just interested in learning more about the research going on in these programming models, I highly encourage you to sign up for that PolyTM workshop in November. And there's links to that from that events page, and I will provide the direct link as well.
Yeah, that'd be great to have the direct link. And besides PAW-ATM, which I know I'll personally be at PAW-ATM, I'm going to be the moderator for the panel this year. So some others of us will be there in person as well. This tutorial, we are going to do a half-day version of this tutorial in person at Supercomputing as well. So if you're going to Supercomputing and you're interested in asking questions in person, slightly different experience, talking during the breaks, and maybe you can show us some of the codes that you're doing, things like that, then it'd be great to see you at Supercomputing.
All right. Well, unless there's any other parting thoughts, I think we can thank the speakers one final time and thank everyone for their time today, and encourage you once again to come back tomorrow for UPC++ at noon and Fortran Coarrays at 1:45. So hopefully see you all tomorrow. Thank you.
Great.